Hey everybody, Jason here from Meridio. Thank you so much for joining today's webinar. Happy Monday to everybody. I hope everybody had a nice relaxing weekend and a nice Mother's Day. Today is Monday, so we will of course be continuing with our sessions with Anthony Grimani talking about audio. Anthony, can you hear me?
Hello everybody.
So Anthony, you and I have been talking now for hours and hours over the last several weeks, and first of all, thank you so much for coming and hanging out today again with me. We've spent the last several weeks talking about, gosh, we've covered so much stuff when it comes to audio. We've covered just general audio 101, kind of basic high-level stuff. We've gone into speaker placements and where do you put speakers and how do you deal with oddly shaped rooms, and we've covered quite a bit here, and today's going to be really cool, something I've been very interested in a long time myself, and I've never really properly learned it, but acoustic treatments. There's a million different types, there's a million different places to put them. Some absorb, some diffuse, some reflect. So let's spend an hour or so kind of talking to each other and teaching the folks that are listening today about acoustic treatments. How you doing over there? I saw your camera just popped up. How's it going?
I'm doing okay. I have apparently a really poor internet connection today, and hearing your voice kind of chop in and out. So I think what I'm going to do when I'm done, saying hello, is I'm going to cut off my my camera and just resort to PowerPoint, safe bandwidth. But yeah, I'm doing great. Nice weekend with the moms of the family, and this topic over here is one that's very dear to my heart. I sometimes tell the story of actually how I even got to where I am here today, and it goes back. What is this? It goes back about almost 35 years ago, in one of the very early introductions of Dolby Pro Logic, in a consumer trade show. Actually, this one was in Germany. The largest consumer trade show is not CES. It's actually Funkausstellung, as it's called, in Berlin. And Dolby decided when I was working there to introduce Pro Logic to the world. And we built this beautiful room, and it was all very nice, but there was no acoustical control at all. It was just all bare walls, and the demo sucked. It did not work. There was no separation. The sound came from everywhere all the time. I think I talked about this several weeks ago. And over the course of very challenging and sweaty few hours, I finally realized, wait a minute, the electronics are working, the speakers are working, the demo tape at the time, it was actually we were using a Betacam SP source. That was all working fine, but the room acoustics were horrible, and the way I fixed that was to actually go back to the hotel and get a bunch of bedspreads off everybody's beds. This was in Germany, so you sleep under these bedspreads, not blankets, and nail them up on the wall, and that's how we did the demo. It was ugly, but it worked.
Yeah.
And so this is here I am working at one of the top audio engineering companies in the world. They have the Dolby Theater now. You watch the Oscars, it's in the Dolby Theater, and only to realize, wow, here I am working here. I'd been there for 3 or 4 years at that time, and nobody ever talked about room acoustics. It was not an issue, and our electronic technology was and still is top notch, and the demo was totally screwed up by what's bouncing around the walls. So I started to read books, talk to people, get really in a transition from just electronics is the only thing that matters to really the acoustics of the work. What I mean by electronics, I put speakers in there, even though like speakers are considered an electroacoustic device. They're part of an electronic chain, and in a lot of people, I mean, a lot of the viewers, a lot of the people I talk to focus on the gear, just the gear. I need a really good speaker, I need a really good amp, really good, and I'm going to put some really good cables and good power cables and all this stuff. It's like, yeah, well, that stuff is important. You got to have decent ones. But if the sound is bouncing in the room around the room is completely out of control, forget it. You may as well have just run down to the electronic supermarket down the street and bought whatever you could buy, because that's all you're going to get. So
yeah, we have a similar thing with video. It's like, you can take the biggest, baddest, brightest projector in the world and you put it in a really bright room where everything's going to look washed out. It's like, what was the point?
no, it's not going to work. Well, somebody may have made a lot of money, but that's not the point. I mean, the client's got to be happy in the end. So I had my big wake up call that one night. I mean, I was sweating bullets. You know, the show's opening that, you know, it's now 3:30 in the morning and I'm freaking out. Things aren't working. Show's opening at 9. Everybody's showing up to see the great demo of the new sound to sound thing. And no, it wasn't working. And so one thing led to another. I learned about acoustics. I then actually met Tom Holman, the guy who started THX. Talked to him for hours and hours. We had a really long conversation. A few years later, he decided to hire me to come in and launch Home THX. But I've been working on this for many, many years. It's not an easy topic. And it's not an easy topic in that the science behind it is difficult. The products are all over the place. And biggest issues, those things you're going to choose are going to be put on the wall where you actually have some aesthetic integration issues with whoever you live with. So it's a triple whammy in complexity. So I'm going to cover all of that in the next hour. Normally that would take 5 or 6 hours, but as usual, I'm going to talk fast. I'm going to crunch it all down, and I'm going to rely on a YouTube video for people to like they went, what was that? You can go back and watch it at your pace. So have no fear. You will be able to get it. It's all in the slides.
And for those of you who are listening, thank you so much for being here and hanging out first thing on a Monday. I do have the question box open in front of me, so if Anthony says anything that triggers a question in your mind, go ahead and type those questions in, and I'll be happy to field them.
Okay, so let's see. I've got my presentation up and running, I think. Jason, can you see that on your screen?
Not quite yet. I have. I just have the camera still. And let me make you the. Let me make you the presenter.
Actually, let me. Sayonara for now. I'm gonna mute out my camera. Bye bye, and I'll come back in at the end.
Yeah, I may do the same thing myself actually. So you should have the presenter.
No, we're gonna miss you.
Yeah, get to see all my DVDs and
show
movies.
My screen. It's a guitar I'm interested in.
Yeah, that's a little beater. You don't want to. You don't want to know about that one too much.
The beaters are great, and that's what I play all the time. Okay, let me know if and when you can see this on your screen.
Okay. And there it is, and that is my cue to mute my camera as well. So everybody watching now, you should have a full screen of Anthony's presentation. So again, feel free to, as we go along here, feel free to type in any questions you might have. So Anthony, with that being said, I see your screen, everything looks great. We're ready to rock.
All right, acoustical treatment selection and placement. That's what we're here to talk about. And suddenly, there you go. My PowerPoint decided to go, so course overview. I always like to start with a 10,000 foot view. So we're going to introduce the science of absorbers and diffusers. There's all kinds of names for these things, but globally, devices you're going to put walls are either going to absorb the sound or scatter it, known as a diffuser. At the end, I'm going to have a whole application guideline. We're going to go through a whole bunch of examples of what we've done on some projects. Big hats off here to my good buddy, Dr. Floyd Toole, whose slides you will see up once in a while from various CEDIA courses and things like that. Warning, this course is intense, so stick with me. So at the end of the course, this webinar, you'll hopefully have understood all the issues of propagation and sound reflections in home theater. You'll understand absorbers, diffusers, base absorbers, etc. And you'll know how to specify solutions for reflections, dealing with echoes, getting the right energy decay, and dealing with standing waves. So a bit about me. I run 3 companies. One, Money Systems, makes superlative loudspeakers. PMI Engineering is another one. I started that 21 years ago. We design and engineer all kinds of media spaces. I'd say 80% are home cinemas. The balance are recording studios, performance halls, and things like that. And one more company called Dimension 4 Acoustics. It's a designer, manufacturer, and seller of acoustical treatments, which is why I love this stuff. So I have a degree in electrical engineering. I spent 5 years at Dolby, 10 years at THX, and 20, actually I should update that to 21 years. 21 years of freedom since then. I've started, my own stuff. I'm my own boss, which means I can work 16 hours a day if I need to. Yay. Overall, 35 years of fun, and I wouldn't trade it for anything in the world. So what else? I was named top 50 industry influencer and top 20 industry personalities by CE Pro magazine. My company, PMI Engineering, has done several designs that have won CDA awards. I've made the top tier a number of times, and along the way invented this thing called Surround EX that was launched with Phantom Menace, the Star Wars Phantom Menace. So I'm a CDA fellow, AES member, I have 6 patents, 2 kids, many guitars, a few saxophones, an airplane, an old British bizarre car called a Morris, bicycles, and too many other toys. So I don't just do this stuff like a geek. I actually get out once in a while and have some outdoor fun, and I recommend everybody do that too. So we're here to talk about acoustics. And why do we want to talk about acoustics? Because they're extremely audible. I like to say that they contribute to more than 50% of the sound quality you're going to hear in a room. So, you know, that's a very, I guess it's really hard to put a real number, but I would just globally say that if you're listening to good sound, half of that is the electronics and speakers, and half of that is the quality of the acoustical environment around your speakers. And you got to tell your clients that. If you're doing a room and you're starting to bring in some acoustical treatments, go, why do we have to put all this stuff in the room? Oh, because it'll just double your sound quality. It'll double your return on investment. Is that I don't really want that. I just say, okay, don't put that on the wall. It's like, okay, so you understand you're going to get half the sound quality, right? And they're going to go, well, the other guy I talked to is not talking about this. Yeah, because he doesn't know, or she doesn't know what they're talking about. So 50% of the sound quality is the speakers. It's really, really key. Now, the cool thing is acoustics are fixable. And if you're in the business of selling AV, you can actually make money at fixing acoustics between the engineer and the products you're going to sell. So I like to describe acoustics as the interface between the speaker, the room, and the listener. So we'll talk a little bit about that. The acoustic interface, I'll show you some diagrams. In an AV system, or just a stereo system, you have source devices that go into preamp decoders. Sometimes people call those a pre-pro. I call them a controller, actually. The output of that on a good system is going to go through equalization products and then into power amps. And that's all under control. The quality of all of that stuff is extremely good today. I'm going to take that signal, plug it into a speaker. It's going to radiate out sound into the room. And if you don't take control of what's going on in this environment, you're going to end up with substandard quality. So that's what we're going to talk about today, is how do you take control of that final acoustical interface. So let's talk a little bit about that. So direct sound from any decent speaker is generally very clear. The off-axis sound can be good too, but the off-axis sound is going to bounce off the wall, and if it's not somehow controlled, I'm not saying eliminate it, but somehow controlled, it can cloud up the sound. So rather than hear a nice round sound image, that's what I'm trying to represent over here, an Easter egg, you're going to end up with a slightly cloudy sound. More reflections cause more clouding, more reflections that are out of control cause more clouding. And in the end, you end up with a royal mess. So with a lot of sound reflections that are not controlled, this is the real key. I'm not saying eliminate the sound reflections. I'm saying take control of them. If you don't control them, you're going to end up with a blurring of image and sound quality through comb filters and other issues. So just think that reflections can distortion. So in this diagram, I'm showing a perfectly good saxophone leaving the center speaker, going to your listener position. A bounce off the wall can make that saxophone look like it's all bent and run over by a car. And I'm using the word can. So again, I'm going to say this probably about 20 times today, which is like, all reflections are not bad. You need some of them. You just can't have all of them out of control. So did you know that at the main seat of a listening room, you actually are listening to more reflected sound than direct? So look at this diagram. The black is the direct sounds. That's the sound that's going from the speaker to you. And then blue are a few arrows of reflections. There's more of those reflections than there are direct sounds. So what we want to do is, again, not eliminate the reflections, but we need to reduce some amount of the reflections, and we also want to break them up so that they're not solid, what's called specular reflections. Ultimately, in a room that's treated, we want a higher direct to reflected ratio than the untreated room, but we don't all want direct. So now I think I've said this about 5 or 6 times about, keep some reflections in there. Now, what the reflections do is 2 things. One is they do blur the sound quality of the speaker. They also tell your unconscious internal 360-degree radar how big the room is around you. The human being is very good at knowing the size of the acoustical environment that's placed around him or her. remarkable, actually. And we learned that from a very young age, that when we're in a small room, there's a certain reflection pattern. In a big room, there's a different reflection pattern. It's all programmed into our brains from a very, very deep level. So if you want to hear the experience of hearing this beautiful concert hall, this is an amazing space to listen to music, Concertgebouw in Amsterdam. This room has its own acoustical thumbprint. When you sit over here and listen to Mahler's symphony, you're going to hear the orchestra. You're also going to hear a bunch of reflections that are the character of the room, and that's your ears and brain at work. And it's a very enjoyable experience because the space is big and the reflections are laid and diffused, and it feels like it's just immersing you in sound. Now, if you go into a small room and you make your speakers play the same concert, your uncontrolled reflections are going to force the perception that that room is only this big. So even though you're listening to a recording of an orchestra playing Mahler's Fifth, maybe in Concertgebouw, ultimately, if you don't take control of the sound reflections, your detection essentially is going to, your internal brainial detection, that's a new word, cerebral detection is going to have a hard time separating the reflections from the small room for the large concert hall. After a certain time, you will work around it, but it takes some brain effort. So we're going to do things to break up that acoustical pattern, that thumbprint, so that you can believe better that you are in a concert hall, that you are in an airplane, that you are in a bathroom, that you are in a lecture space, that you are outdoors, that you are in space, although in space there's no sound, all of that. So the sound field will be room limited, and we're going to work to break up that reflected character so that you can actually believe what's coming out of the speakers. Jason, are all these slides coming through okay, and am I sounding okay and not too robotic?
Yep, everything's really good so far. One thing I just wanted to point out, just because I've seen this for years and years and years, and I always get a chuckle out of it. I'm sure you do too, and everyone listening does too. You know, I run into these AVRs all the time, and they have all these like simulated modes, you know, like Hall and Vienna and things like that. And are they just trying their best to kind of mimic what that room might sound like with some wacky preset? Is that kind of the idea? I mean, they've always sounded silly to me, so I've never ever used any of them.
Yeah, so I would say that's a laudable effort by a bunch of acoustical engineers to go measure these spaces or simulate them and put an array of reflected sounds in the surround speakers. You know, there's a few companies that have many extra loudspeaker outputs, and they're trying to simulate that reflected energy character from those spaces. And you know, some of them do. Some of the better algorithms do a pretty good job. There's some really high-end solutions there at the professional level that have existed now for a few years.
Oh wow!
Probably the first one was Lexicon Lares, Lares, in which actually a guy called David Griesinger at the time had created a bunch of algorithms to simulate, out of a large array of loudspeakers, lots of little speakers placed around you, the sound of pretty much any space. And you could actually be in a room that was like 40 feet by 30 feet, and David could push a button and you'd swear you were in a large concert hall.
Wow, that's
cool.
And
it took a ton of signal processing, very intelligent decorrelation and things to make it sound that good, and lots of speakers in a careful acoustical environment. The idea there was to dry out the space you're in and replace all the reflections by what's coming off of the speakers, and worked really well. Some of the simpler ones, I'm going to use the word gimmicky. I don't want to put it quite that way, but they don't work quite as well. I would say try it out. If you like it, you know, have a good time with it. Sometimes it just sounds really fake and synthetic to me.
Yeah, just being the purist I've always been, I've always either used the straight mode or the 7-channel stereo mode, and that's it. I don't really mess with those other modes. But interesting to get a little bit of background on it. Thanks for touching on that. I've always been curious about those.
Yeah, those again at the professional level, they actually are used professionally to make small and mid-size concert venues sound bigger. That's their main application, is to try to give a sensation of a bigger sound space. Okay, so let's continue on this. Again, I'm going to do, as usual, I do a little bit of background info and then kind of get into the actual products and solutions. So what we are looking at generally in a room with no treatment. So I'm basically going to assume that everybody that's sitting here listening to this says, hey, I've got a room. I need to know how to treat it. I need to know if I need treatment. I need to be able to convince my client to treat it. And by the way, you know, if your client has enough attention span to sit through this, I can do the sales pitch for you. Essentially, just go, hey, listen to Anthony ramble on about the stuff, and you'll understand how important it is. So here's a room with no treatments, and we'll just put sound out of the center speaker because it's the easiest thing to do. So there's a direct sound. There's reflections of the off axis of a speaker. So got to understand that a speaker doesn't just send sound directly in front of it like a narrow beam. It also radiates out plus and minus X amount of degrees depending on the speaker. But on the better speakers, they radiate out a full 90 degrees in this direction and full 90 degrees in the other direction, full band. So off the right side of the room, the sound that's off 10 degrees and misses your head bounces around a few times and comes back to your head a little bit later. The sound that's off 20 degrees from axis bounces around the room, comes back to you a little less later. The sound that's here 30 degrees bounces here 40 degrees, 45 degrees bounces, 50 degrees probably has a single bounce off the wall, et cetera, et cetera, et cetera. So this is just an expanded version of what I was showing earlier. And as you can see, there's one direct sound from the speaker to the listener, and there's a bunch of off-axis reflected energy that produces a lot more return pings to the head. I love that word, ping. It is kind of like a, you know, sonar ping or a ping on a computing system or network system. So that's just the right side. Now we'll add in the left side of the room, and you can see all of the red pings. For those of you who are not colorblind, all the red pings compared to the green ping. So there's a lot of red pings, a lot more reflected energy, and if you don't do something about it, chaos reigns. Okay, so let's look at what we're going to do now. Interestingly enough, even in a room like this with a lot of reflected energy, you still get the sensation, even though you're probably getting 2 or 3 times more reflected energy going into your ear. I've got a slide coming up that's going to restate that, but realize that this total energy coming off the red arrows is often 2 to 3 times more acoustical pressure into your eardrums than the direct sound. So even though you're getting all this reflected energy, you still interestingly have the perception that the sound's coming from here. And why is that? There's a psychoacoustic effect known as the Haas effect, whereby your ear brain, when it hears all these reflections, tries to figure out which was the first arriving one and locks on that one, kind of like a sonar ping. I'm trying to look for it now. It basically go your internal brain robot goes, that was the first one that got to me. That's the originator of the sound. That's the one I need to look at. And that's a very, very primal process. That's the one that keeps us from being eaten by velociraptors in a forest. It goes back that far. Those of us who did not have that instinct got eaten. Did not reproduce, did not generate offspring, are not here anymore to tell the story. So even though you have all these reflections, you can tell that the sound's coming from over there, but your brain is the one that's processing all that through. And you can do it for a single person speaking in one loudspeaker. When you have an immersive audio system with 15 speakers all the way around you, bouncing reflected energy in all directions, your brain just goes, dude, I give up. I can't tell, which is exactly what happened on that demo in Germany back in 1987, if I remember right. So it takes brain power for all of that to work. It's fatiguing. Don't do it. Now I'm going to get a little scientific. This is an impulse, what's called an impulse response, which is an analysis of how these pings hit your head from a speaker. So if you put out a ping from a speaker, there's a direct sound that gets to your head. And then later in time, there'll be some reflections. So maybe these could be the ceiling and floor. These could be the lateral first reflections, maybe a left, right, and back wall, and then there's second reflections, and these clusters of reflections, and eventually, over time, it all ends up being a schmear. That's the thing you put on your bagel. No, it's a smear of sound reflections, but this is a problem. This sound gap, ping, gap, ping, gap, ping creates a fair amount of it results in poor sound quality because you hear all these different little reflections, or your brain receives them. You don't actually separate them out until further, but you got to smooth that out. Ideally, what we want is a reflection pattern that's like this. So 2 things between these slides. I guess it's not too visible. Is that the reflected energy, you want to pull it down somewhat and you want to smooth it out so that the reflected energy is still in the room, but it's scattered out more evenly. A room that has an impulse response decay like this will sound better than a room that has one like that. So we're going to look at how we get there. One solution to treat this is what's called absorption, which is some material that scrubs off the acoustical energy. It's like an audio sponge. It's typically a fibrous material. Sorry, let me go back to this. It's typically a fibrous material that converts the energy into heat through friction. I'll show you a slide on that in a second. Another way to treat that is what's called scattering, in which rather than absorb the sound, you break it up into smaller pieces so that it still stays in the room, but rather than have a strong reflection to you like a mirror, it's a diffused character. And really the right solution that we're going to get to, towards the end of this presentation is the right combination of absorption and scattering. Now, sometimes people do this. I see this a fair amount in recording studios, and once in a while I see this in home cinemas in which the project was not conducted, I would say, carefully or scientifically, or the person who built it didn't know what they were doing. Is they eliminate all the reflections. They go, hey, if these sound reflections are bad, let's just kill them all. And they just put an inch, 2 inches, 3 inches of fiberglass everywhere. So from front to back, floor to ceiling. Well, so what? So what's the problem with it being dead? Now you're hearing the speakers, right? You're hearing the sound directly, just like headphones. I'm listening to your headphones. You sound good. What's the problem with that? So everybody seems to know that dead is bad, right? And why is dead bad? Why is dead bad? And dead is bad because humans have come to expect a certain amount of reflection from when you're just a very small child. Your brain slowly programming through, I guess, the cerebral equivalent of fuzzy logic is programming to seeing a room, looking at where the parents are, and also hearing reflections so you can learn how to eliminate those reflections in your echo canceling program in your brain. If you get rid of all of those, if you put a person in a room that's all dead, it contradicts your brain function. So you need to preserve some reflection that is correctly set up so as to support your loudspeakers. Okay, so this is now the 10th time I think I say that you don't want to kill the whole room. Okay, I think you guys got it, right? Not too much of the stuff, just a little bit. It's like salt or other spices in your food. A little bit is good, too much of it, and it's throw the food out and start all over. So what do we want? Ultimately, I'm going to give you the summary now, and I'm going to go back and build the information on this thing iteratively. Ideally, what we want out of a good room is we want the direct sound of the speaker. We want a good speaker producing a sound wave that travels through space or propagates through space, goes to our head after whatever time it takes, 10, 12, 13 milliseconds. And then we want reflections in which some of them are absorbed, some of them are scattered. Some are absorbed, some are scattered. Some are reflected, some are scattered. Ultimately, a listening room or a cinema room that sounds good is one that has reflections, but they're turned down about 20%, 15 to 20%, and they're scattered a certain amount. If you can actually produce a sound field that does this, where there's direct reflected energy and all the off-axis energy of the speakers is either absorbed or scattered, you're going to end up with something where your client's going to go, wow, I really hear the dialogue clearly, and I hear the sound effects, and the sound stage is huge, and wow, this is great, thank you very much, here's my check. And I'll tell all my buddies, in fact, I'll have all my buddies come over right now, and we'll have a movie night. I'll give them all your business card. So
good advertising.
Good advertising. So we want a smooth sound field. We also want, and I'm going to talk about this a little bit later, we also want some binaural dissimilarity, low interaural cross-correlation. So not only do we want less sound reflections, but we want the sound reflections from the right wall to be somewhat different to the sound reflections from the left wall. And I'm going to talk about this a little later. So if you do all this, you'll end up with this perceived character, which is there's a direct sound and the room is immersing us in a wonderful sound field, a nice crescent of energy, a nice buttery croissant of sound energy. So here's the acoustic recipe. Here's how you get there. There's a simple explanation, and then I'm going to spend the next half hour geeking out about all the science on it. So in order to get to this thing I just described in the slides before, all you need is about 15% of the left wall, the right wall, the back wall, and the ceiling covered with absorption. Only 15%. So if you're just to do the math, if your wall is 200 square feet on the left, what's 15% of 200 square feet? This is a little quiz for Jason. Quick, 15% of 200 square feet.
10% is 20, so add another 5% to that. You're talking about 25%.
Close.
Did I do that too fast? I may have done that too fast.
Pretty close. 10% is 20, 5% is 10. So you need 30 square feet on
30,
the left.
sorry, yeah. Sorry,
Okay.
there you go.
So that's all you need. If you do more than that, if you actually do more than 15% absorption, the room's going to start to be too dead. And like Jason said, it just doesn't sound good. It doesn't sound good. It sounds bad. It doesn't sound good. So now I've said it about 20% of the, I don't 20% of the time. 20% of the time I've been talking, I've been saying don't put more than 15% absorption surface. So you want to lower the reflected energy by about 15. In some rooms, it can take up to 20%, but something around that space. You want to distribute those absorbers evenly around the left wall, right wall, back wall, and ceiling, not all cluster them all in one place. That's not going to work. The other thing you want is about 15% of scattering surfaces. I use the word diffusion. Really, the true term should be scattering, which is surfaces that have broken shapes. There are lots of purpose-made materials that are from lots and lots of different vendors. I'll show you a bunch of pictures later. 20%. So you want to interleave those with the absorbers. Don't put all the absorbers in one place and all the diffusers is another place. The brain's not going to be happy with that. You want to kind of have an absorber, a diffuser, an absorber, an diffuser, an absorber, a diffuser as you go down the left wall. Same thing on the right wall. On the back wall, you can put more absorbers in the middle if you want. There's some good reasons for doing that. There also are there's lots of different types of scattering devices, but I loosely cluster them into devices that take the sound and scatter it into 2 dimensions. And I call that a 2D diffuser. And the D here does not refer to the quadratic residue equation, which is known as 1D here for that, but I call this as a device that breaks a sound into a plane, and I will show you plenty of diagrams of that later. So 2D diffusers in which the oncoming sound is turned into a horizontal plane, and 3D diffusers, I'm sorry, those go towards the front of the room. 3D diffusers in which the oncoming sound is broken into a hemisphere. You put those generally towards the back of the room. It improves spaciousness. It makes the absorbers work better. It smooths out that decay curve. That's what you got to do. Don't forget to treat the ceiling. Some people do the walls and the ceiling is forgotten. Some people do the ceiling and then do the walls, and sometimes it's a requirement from the client. Sometimes it's just, hey, I forgot.
That happens in video too a lot, by the way. They'll darken the sidewalls and forget to darken the ceiling or the floor. I see that a lot too.
Right. Yep. And the ceiling is the closest surface, and it's a real big problem for video. I've actually measured on ANSI patterns. I've measured a 40:1 contrast ratio from a room with a light ceiling out of a projector that can easily do, well, that claims 50,000, but in reality could easily do 3,000 to 4,000 on true black to white, which is excellent, by the way. That's beautiful contrast ratio. And you put a white ceiling and it's all washed out to 40 or 50:1. So to your point earlier, here you are, you expect a really high-end projector with a high contrast ratio, and it behaves barely better than a commercial presentation projector that costs 1/10 of the price.
There you go.
And is, as you know, as 1/4 the size. And ultimately the client's looking at a poor picture and is not happy. So don't forget to treat the ceiling for both dark tones in the video, and then acoustical absorption and diffusion. So don't forget base absorption. So I'm going to talk about that. The absorption needs to be broadband. You need to cover everywhere from the lowest frequencies to the highest frequencies, and there's a whole module on that. So without further ado, let's talk about absorption. So first off, there are lots of different types of absorbers. The most common ones are called frictional. They work through friction. I will show you a diagram of that. There's other ones that are called flexural, in which you're flexing a membrane. The flexing of that actually dissipates energy through heat. Some of those are tympanic, so they're not just flexing, but they also flex over a relatively narrow range of frequencies because they're resonant. There is also Helmholtz resonators that are like giant wine bottles. When you're done emptying a bottle, you can blow into it and it resonates at a certain frequency. That resonance is actually an absorber at that frequency. There's also what I call a perforated filter, which is a bit of a combination of the above, which is a Helmholtz absorber that's pretty damped out, so it works over a broad range of frequencies. But rather than have a single hole, it's multiple small holes that are in front of some kind of frictional absorption. So lots of different types, and I'll talk about what you use where. First of all, let's look at the most common type called a frictional absorber. If you put some on the side of a room and there's a direct path and there's reflected energy, if the absorber is the right type and thick enough, virtually nothing will go back to the listener. That frictional material scrubs off energy through well, it's a frictional absorber, so it scrubs it off through friction, but literally the air particles that are moving and expanding and compressing and actually have a velocity, they are actually moving, they meet typically either fibrous materials or some foam materials, but they meet all these they basically bounce off all these little hairs, all these little cells, these walls of the cells, and at every bounce, they scrub off some energy, just like you would if you were scrubbing a piece of furniture with sandpaper. It's not much more complicated than that. Now, that's what it looks like. So the air molecules are going back and forth. This is a fibrous material or a relatively, relatively scraping material. Fiberglass is great for that. If you want to feel what that feels like, take a big chunk of fiberglass and rub your forearms with it. And no, don't do it. Do not
No,
do
don't.
it. You'll
Yeah,
hate
don't do
me
that,
for it.
guys. Don't do that.
Don't do it. Don't try this at home. What next? I'm going to tell you to, just try chlorine for COVID. No.
Yeah,
Don't
just
try it.
Anthony,
Yeah.
real quick, there was a question that just popped in from Mike. He says if 15% of the surface is diffusion and 20% is diffusion, is the rest of this other 65%, is that just bare surface?
Yeah, absolutely. It's just the
bare wall,
original
right?
wall. So reflection. Some people want to sell you reflectors. If you're willing to buy reflectors, I have this beautiful bridge I can sell you over here, and I'll also put some air from right outside here and sell you a big can of that. You don't need it.
Yeah.
You don't need it. So absorbers, diffusers are what you need. And yeah, correct, sir. That's how much a basically untreated reflection you want in the room. Now, you want to control where that is, and I'm going to show you that a little bit later.
Yeah, the
Okay,
where, that's the amount. Now it's the where. Where do you put them?
it's the where. That's where it gets really interesting. So now, absorbers coming in all different types, but they should have an absorption coefficient that's even at all frequencies, or actually sometimes you can taper it down at high frequencies. I'll talk about that a little later. So an absorption coefficient is actually a measurement I'm going to show you. If you're buying materials from any vendor, you should ask for the absorption coefficients. It should be somewhere on their website, or you should be able to download it or have them send you, and it should have been tested in a reputable chamber. So that tells you how well the product works. Note that if you take a panel and you mount it with a bit of an air gap away from a wall or a ceiling, it actually works to a lower frequency, and I'll explain that too. So panels come in all kinds of different thicknesses. A 25 millimeter panel, which is 1 inch. You'll notice me being very metric centric on this presentation.
Sure.
And it's because I think metric works better. But 1 inch panels work down to 1 kilohertz. It's okay. It's not great. Some people go, no, you're going to screw things up. That's not enough. Where's 1 kilohertz? 1 kilohertz is in the middle of the audio range. It's actually above the middle of a piano keyboard. If you take a piano keyboard and play a note right in the middle, that's a 440 hertz. So 1 kilohertz is above the middle of the piano keyboard. That means that the bottom half, or more than the bottom 5/8, is untreated when you do just 1 inch panels on the wall. 50 millimeter panels, which is 2 inches, work down to 500 hertz. That's better. And 100 millimeter panels, which is 4 inches, work down to 250 hertz. That's what you need. And then what happens if you go lower? Well, the return on investment is not quite so good for direct reflections. The ear brain doesn't really notice those too much. So you can go thicker. You can go to 6 inches, 150 millimeters. But the return on investment is not as good as doing other things. So ideally, if you're doing good work, you should have panels that are up to 6 inches, typically 4, and don't do things that are just 1 inch, because it's just not good enough. And that's kind of a graphic of it. In reality, this is a real test from Owens Corning 703. That's a mid-density fiberglass. It's tested at, I forget which chamber here. The original source of this showed it, but this is actually what happens. This is a measurement of the 1 inch material. So it has absorption of about 1 up right around here at 2 kilohertz, and then at a lower frequency, when the wavelengths get long enough, the absorption starts to fall off. So by the time you get to 500 hertz, the absorption coefficient is about 0.6 or 0.65, so it's lost close to 40% of its efficacy or efficiency. Now, absorption coefficient is an interesting thing. I could talk about that for about an hour or two and talk about the different measurements and whether it's on axis and off axis and free field and this thing and that thing. But I'm just going to say an absorption coefficient of 1 means that the material is absorbing all the sound.
Right.
And as a reference, an open window, an open section of wall has an absorption coefficient of 1. It's not actually absorbing, the sound's going right through, it's not reflecting. Okay, so if you're trying to figure out what's full absorption, it's like there's when you put a panel on the wall, that's like cutting a hole in the wall, the sound's not going to reflect off it. Okay. So absorption coefficient of 1, pretty good over here. Now you take a 2-inch version of Owens Corning 703 and you measure it again, and look at that, it gets a little bit of an extra bump here and works really nicely down to 500 hertz and then falls off. It also has a higher absorption coefficient, which you go, wait a minute, if it's an open window, it's an open window, it's an open window. And that's an idiosyncrasy of the measurement method in the chambers where they measure this. A 2-inch panel has more side area than a 1-inch panel. So the absorber is not just only absorbing in the front in like a, if you had a 2x4 absorber, if it's a 1-inch thick one, the 1-inch band will absorb a little bit. If it's a 2-inch thick one, the 2-inch side will absorb somewhat. A 4-inch thick one will have an even higher absorption coefficient. So it absorbs more than an open window, which is impossible. It's just an idiosyncrasy of the measurement, but it does tell you something about how more efficient a thicker panel is. So this is 3 pounds per cubic foot, Owens Corning 703. Here's more measurements actually showing 1-inch, 2-inch, 3-inch, and 4-inch. There again is a 1-inch. Here's 2-inch. Here's the 3-inch, and here's the 4-inch, where you can see that the 4-inch works really nicely down to 200 hertz, and that's really good.
It's so interesting how hard it drops off too after it hits that peak.
Yeah, and there's a whole bunch of factors. This is where I say I could talk about that for an hour or two.
Sure, of course,
a lot of reasons. There's a lot of reasons for this funny bump over here, and for the extra gain, a whole bunch of different things. But bottom line is, if you're doing a really good theater, if you're putting expensive speakers and a client says, I want really good sound, good dialogue, clarity, really impactful stuff, your mind should immediately go to, I'm doing 4-inch, 100-millimeter absorbers all over these walls. And if you want an extra little boost, you can go to 6-inch, but right around 4 inches is a great return on investment. So floating an absorber panel, so if there is no budget or if there's other reasons to not do 4-inch materials, but you have the space, you actually can take a 1-inch panel and stick it on the wall with a gap of 1 or 2 or 3 inches, and you'll get more absorption at low frequencies, a little less at high frequencies, which is actually kind of good. Most rooms have too much high frequency attenuation in their reverb field, and that works more better. So absorption away from a wall, high and low frequencies are tamed. High frequencies, I don't know who wrote this, I did, whoops. Anyway, this is more low frequencies are absorbed over here. So that's a trick, especially on the ceiling. So one of the things I love to do is when you put panels on the ceiling, is actually use a 1 or 2-inch panel, leave an air gap behind that, and put rope lights, put LED rope lights behind that, and use that as an indirect lighting source. Not for when you're watching movies, because it's going to wash off your screen, but for entry and exit, for ambience, it's a very cool way to light up a room. Okay, this is a slide from Floyd Toole. True or false? Acoustical treatment begins with the elimination of all first reflections. False. False. There's a lot of people there who talk about, hey, I'm going to absorb the first reflections. Nope, sometimes having a little bit of first reflection is good. It depends on the room, depends on the conditions. So if you always go with the approach of treating the first reflection, you will end up sometimes with the room sounding unpleasantly dead. It's not always the right thing to do. So some of that reflection is needed by your ear and brain, okay? So now I think it's the 21st time that I say don't absorb everything. Recent research found that even recording engineers adapted quickly to very different rooms, reflective, diffusive, absorptive. So you do adapt. It's really amazing. You can put a person in a room, and after a few seconds, their ear-brain process processes out the reflection. I
Sure.
contend that 2 hours of watching a movie with that is less pleasant than if the room is just properly treated,
Oh yeah.
more relaxing. Um, you don't have to try to listen through to the sound. You may as well treat the room. So, conclusion: it is optional to treat the first reflections if you have good loudspeakers. I'm sorry. What Floyd is saying here is you have good loudspeakers, which are those that have a good off-axis response. You may not have to worry about the first reflections, but treat the other ones. If you have bad loudspeakers, you may want to treat the first reflections. And what I'm calling a bad loudspeaker is one that has a poor off-axis response.
Right.
And then Floyd's making a little smiley face that, hey, if you're selling absorbing materials, you want to put it everywhere. And I sell absorbent materials, and do not put my absorbent materials everywhere, please. Only 15%. All right,
Right.
so now it's 22 times. Okay, so Floyd's pointing out that well-furnished normal living spaces, especially sort of slightly more classic spaces, not modern minimalistic spaces, but kind of traditional spaces that have carpets and furniture, sofas, drapes, bookcases, they typically naturally have enough stuff on the walls to meet this criteria of reflection decay time called 0.5 seconds of decay time. I'll show you that a little bit later. And so if you're putting speakers in a room that you walk in and it looks like it's got a fair amount of trappings of regular life, you may not need to worry about it too much. You clap your
Good
hands, you may
point.
notice it doesn't sound too echoey. Maybe it's just fine. And how can you tell if it's just fine? Is, if you are a geek like me and you've bought a test microphone for $70, that's all it costs to get into the Geek Club, and you download a Room EQ Wizard, you can actually measure the reverb time using the speaker itself. So you can put a sound to the speaker, measure the decay time, and see what it is. That's what your client's actually hearing. If it's somewhere around 0.3 or 0.5, you don't need to do nothing. All right, now, custom home theaters don't have all of that stuff. They don't have big bookcases, couches, carpets, and so that's where you start to have to bring in things to treat the room. So what Floyd says is they need to be artificially furnished. Okay, so let's take another look at what's actually happening off that reflector. What is the effect of a sound reflection? So here's our 2-inch absorber in a kind of very schematic form, showing its absorption character. So here it is absorbing down to 500 hertz and then falling off. So that means that everything above 500 hertz is absorbed. That also means that everything below 500 hertz is reflecting off the wall, right? So this is the sound absorption. That's what the thing is sucking out. But if you're sending broadband sound to the wall, this is what's bouncing off the wall. You guys follow that? So this is what's absorbed by the panel on the wall, and what's left over is everything that's not that, right? So this is what's reflecting back to your head below 500 hertz. So let's see what that does. Here's by the way, all these diagrams are from Floyd Tool, and this is a very well-designed loudspeaker in the JBL line, made mainly for professional applications. And by well-designed means it's a good broadband speaker, has good frequency response, but it also has this funky thing up here that looks like this, sideways cross. This is a waveguide. There's a compression driver, 2-way compression driver in this waveguide. And the role of this waveguide is to disperse the sound horizontally and vertically to where it's very, very constant with frequency. What that means is that the sound that bounces off the walls is a complete replica of the direct sound, which is actually good. If you have a speaker in which the dispersion is not very even, what's bouncing off the wall is a distortion of the direct sound. So that's not as good. So this is a good speaker from JBL. My company, Grimani Systems, in making its speakers, does the same thing with a very different form factor, but same thing. The reflected energy is going to be an ideal replica of the speaker. So your brain's going to go, aha! I hear a direct sound. I can hear that that's slightly late. It's a perfect replica. I will ignore that. Now, when you put a 2-inch panel on the wall, what that panel is going to do is absorb only 500 hertz and above. And Floyd has this really cute diagram that shows that speaker is going to sound like it's got a smaller waveguide. See, the speaker is still the same from 20 hertz to 500 hertz, and above that, the waveguide takes over a little bit higher, but above that, the way it just sounds quieter. So what that wall has done, that 2-inch material on the wall, is just turned down the high frequencies of the reflection.
Right.
Okay, that's not a good idea. Okay, so if you do 1 kilohertz, it's even worse because you've only turned down everything that's even higher. So it is better to do a 4-inch absorber or a 6-inch absorber, so the whole speaker is turned down. I just love this graphic that Floyd's come up with. This is very Floyd, very cute how he does his diagrams. Good, not good, and and actually good. That is
Right.
okay as a first reflection. I'm not talking about the overall reflections in the room. So good, not good, and then finally good. Just turn the overall thing down.
It sounds like it's a linear thing. You want to turn it all down at the same way, the same time, right?
That's exactly it. You want to turn it all down. Now,
Right.
all would mean turning it all the way down to 20 hertz. And as it turns out, the ear brain doesn't really need that. What it does need, there's all kinds of studies for what you notice, and you really need to get down to 250 hertz. And below that, it's a return. Again, the return on investment is diminishing.
Sure.
It's good. I mean, if you can control it all the way down to 100 hertz, that would be being obsessive. But that's the same obsession in acoustics that it is to put really special speaker cables and putting expensive power cables and all funky, expensive connectors. If you're willing to obsess at that level about the interconnections and the electronics, then you should obsess about the room reflections all the way down to 100 hertz, because it has a way bigger, way bigger effect. So if you look at this a little more scientifically, I'm looking at my watch again. Here I am an hour into it, and I haven't started with the actual absorbers, but this is all good. What I'm going through is stuff that you won't normally see out there on people's specs and websites and stuff. You'd have to sit through either a CEDIA or AES presentation. So I hope this is worth it to you guys. By the way, how many people do we have today?
Right now we've got 11 total.
Okay, cool. Well, hey, you 11 guys, let me know if you need to drop off. If you do, I understand it. If you can hang with me, that'd be great. Remember, this is being recorded, so you can also watch it later on either the YouTube site, or I think there's another place I've noticed where you have it. So let's take a look at the diagram, the response of a speaker. So this is the axial response of a very good speaker. I actually happen to think it's the speaker we had in the diagram before, but hey, and this is the off-axis. This is the sound power. This is the net energy going into the room, and this is actually the reflected energy. So this is the first reflections, that one in red. You see that right down there. So this is the response of what's actually hitting the wall. So when you put an imperfect absorber on the wall, this is what's going to come back to you. So no effect below, what is this, 9876. So no effect below 500 hertz. And then above that, absorption not very even. So that's what you're going to get coming back from the sidewall. And what you ideally want is this. You're getting that from an imperfect absorber on the wall. So what do we do to avoid degrading good loudspeakers? You want thicker fiberglass or acoustic foam, no less than 3 or 4 inches. More thickness is better, not more absorbers, but more thickness. So that being said, you see this diagram over here. There's a lot of vendors out there that sell acoustic foam that looks like this. And I love that Floyd wrote here. Remember that sculpture acoustic foam has to be twice as thick as slab flat acoustic foam because half of it's air. So the manufacturer's taken out half of the foam over here, sold you 2 panels for the price of one. Well, guess what? They work about half as well at the low frequency. So these thicknesses apply only to things that are chunks of fiberglass or higher density foam. They don't apply to sculptured foam, where you basically have to multiply that number by 2. In other words, don't bother with stuff that looks like this. It don't work so good in perfect American English, Americanish, like I've heard it called.
That's Anthony, too. The funny thing is I see that a lot, like in DIY theaters, especially. People go on Amazon and just order like 97 cases of this stuff and just slap it everywhere, and they think that that's acoustic treatment.
Oh, it's horrible. I've seen people in studios line up the whole front wall with this stuff. The whole front wall. So what's on the front wall is what radiates to the front wall is the low frequency of speakers. Speakers don't radiate mids and highs back from them. They radiate low, and they'll put 1-inch foam like this, which absorbs 2 kilohertz and up on the
Mm-hmm.
wall behind the speakers, and it has no effect to the back of the speakers. All that it does is it captures a reflection after it's passed your head, bounced off the back wall, come back and absorb only 2 kilohertz and above. Total
Right.
waste of time. It
Mm-hmm.
makes it look very, very pro, but it actually doesn't work
It hurts. Yeah.
for nothing. So other notes on absorption is don't over absorb. I think this is now the 23rd time I've said it. Dead rooms sound odd. Our target reflection decay time, which I'm about to start talking about, is about 0.3 seconds. So when you put sound into the room, it should reflect around and bloom around the room. In smaller rooms, around 0.2 seconds. In bigger rooms, around 0.5 seconds. The average is around 0.3, 0.35. That's a good decay time. Oh, typo. Let's correct that typo.
Uh-oh. Good call.
Live
Good catch.
in person. Yikes.
Hey.
And now back to our program. So, dead room sound odd, target reflections here, 15% coverage of wall surfaces is all you need. And then you got to hide it. So we're going to start to talk about this thing of aesthetics. I'm going to start to bring that more into the presentation. But, this stuff doesn't look good on the wall. It's a bunch of warts sitting on the wall and the ceiling, so a very techie client may like it if you do a very linear layout where things are very evenly spaced, which may not be the best for acoustics. It may look okay, but basically this stuff don't look good. Ideally, you want to hide it behind acoustically transparent decorative fabric. So you line the walls with essentially an upholstery fabric that has to be acoustically transparent. There's different fabrics out there. Some of them are essentially like grill cloth. They let all the sound right through, and just looking at the panel doesn't tell you everything. There's some fabrics out there that are very thick but are woven very loosely that let all the sound through, and other ones that are very tight weave and not very thick, and they don't let anything through. So saran wrap that's very lightweight doesn't let any mids and highs through, so don't use that. Okay. Other ways to hide the stuff is you can do custom prints. So we've done rooms in which the panels on the walls are actually a network of printed panels, or you actually print a whole wall worth of a sand dune scene or a forest scene or whatever you want to do. And then you put that in front of the absorbers and diffusers. There's also some plasters out there that are porous from about 4 different vendors that you can put on the ceiling, so you can treat the whole ceiling with that. And it works, just don't do everything absorptive out there. Again, that would over absorb it. There's perforated woods, slotted woods, perforated sheet metals. There's a whole bunch of different materials you can cover the absorbers and diffusers with to not let them be ugly warts on the walls. Jason, am I still sounding okay? Am I distorted? Am I clean? How's it going?
Yeah, Anthony, we've had a couple of like half-second hiccups, but only a few. Everything's fine.
Excellent. Okay. So a quick note on acoustical fabrics. So Guilford of Maine sells a lot of upholstery fabrics, and they actually have a listing that shows acoustical fabrics, some of which don't work at all. I don't know where they come up with it. I've talked to them a number of times. We've measured a bunch of them. Among their best is what's called FR701. That's acoustically transparent up to about 10 or 12 kilohertz, and above that it starts to attenuate. That's not bad. It's that means that the reflections off all the walls are going to be okay. And you could argue that maintaining some reflected energy in the room as a specular character above 10 kilohertz is fine. There's other fabrics they're making, notably what's called Carrara, like Carrara marble. That's an absolutely beautiful fabric. It stops transmitting sound above, I think, about 1 kilohertz. So this is a measure of how much sound gets through. Just be really careful. So you got to make sure the fabric is acoustically transparent and doesn't introduce any attenuation. It needs to be at least up to 6 kilohertz, preferably 10 kilohertz for a really good room. So if you're covering front speakers with the fabric, either fronts or sides or backs, you got to make sure the fabric is transparent up to 16 kilohertz, and you can measure it. You just put pink noise on a speaker, get that geeky microphone you just bought to measure reverb times with, or reflection decay times with, measure the speaker alone, and then measure it with a piece of fabric between the speaker and the microphone, and you can tell the difference. It's not that hard. So now absorber panels come in all kinds of different shapes and forms and thicknesses and types and materials. They can come with rounded edges, square edges, beveled edges, you know, whatever. I will warn you that most of the panels that have these sculptured edges are done by hardening all of the edges or putting a plastic form around them to form that. That also means that this entire side is now no longer absorptive,
Right.
which is a pity because you're losing between 15 and 20% of the absorption capacity of the panel. So if you can get away with the regular square panel with soft edges, you should try to do that. Okay. Now, a little bit of shameless shameless plugging, but I'm going to do it anyway because people may as well know. We make a bunch of different absorbers and all kinds of different types. This is our highest end absorber called the Dimension 4 Symphony Absorber. It is a 4-inch thick combination of mineral wool and fiberglass that's very high absorption coefficient, but it's placed in a vented enclosure box. The sides are absorptive up to about 2 kilohertz. And above that, they reflect the sound, and that's so that the high frequency, where's that said? Oh, I don't have that anymore. The high frequency energy is actually scattered off the side of this box. And what that does is gives us a really good absorption coefficient down to about 200 hertz, and above about 2 to 3 kilohertz, it doesn't turn off, but it tapers down a little bit so that the room has a little bit more high frequency reverb in it. Most rooms have naturally a loss of high frequency reflected energy above 2 to 3 kilohertz. And by doing this, which is more expensive because you got to, you know, do this perforation and all stuff, by doing that, you end up with a better performance. If you're the type of person that's obsessing over, again, speaker cables, interconnects that are expensive power cables, power conditioners, and all of the tweaks of audiophilia, this is what you deserve to put, or your client deserves to put on the wall, is a thick absorber that doesn't absorb too much high frequencies. And you do that, and the air in the room will be wonderful. All right. Other materials we make are in the line called Sonatus. This is what we call the Leviter, by the way. It's a dense polyester foam with a flocked finish. It comes in 2 varieties, 8 centimeters and 12 centimeters, which is about 3.5 inches and about 5 inches. It comes in many different colors, and it works from 250 hertz to 12 kilohertz for the 12-inch version. It comes in black, white, black, gray, white, blue, red, yellow. That's about it. We also have this funny group of products called a Decozorber. So this is essentially the same material as what's inside here, but instead of being flocked, we apply a panel of wood that makes it decorative. So if you imagine a whole network of this stuff on the wall, it can actually look really good. This also tapers down the high frequency reflection. So this is gets a little bit better low frequency absorption because it's a bit of a tympanic absorber. But this form scatters a little bit of high frequency and tames down, just like the absorber I showed earlier tames down the higher frequency. So dense polyester foam wood finish, it's 60 by 60 by 8 centimeters, which is 24 by 24 by 3.15 inches. It comes in many finishes, and it works from 200 hertz to about 5 kilohertz. Above that, the energy is largely bouncing off the front of this, which is kind of good. To preserve some high frequency energy in the room. Again, there's different finishes. This is one style called the Eva. This is a style called the Quad in walnut. This is the Quad in wine red. This is what's called the Maze, which is more of a low frequency absorber with even less high frequency. So go to the Sonatus USA website, you can see it.
Anthony, real quick on the Quad, for example, or any of them for that matter, like the size and the shape of those decorative, designs or openings or whatnot, would it change the acoustic characteristics of the panel if those were different? I'm just curious.
Yeah, so this has a different high frequency reflection than this. This absorbs down to lower or reflects more high frequency energy than that. Okay, so you got to be careful about where you use that. We tend to use this more towards the front wall of the room where you don't want to absorb too much high frequency. You want to tame mainly the lows. Or we'll use this in rooms where we know from calculating the reverb of the room, like if there's a lot of carpeting, where there's a lot of absorption of high frequency, we'll use more of these guys. And so I'm going to get to that. Good question. So that
Cool.
has a different high frequency pattern than this. This is kind of in order of high frequency reflection. This has the least high frequency reflections, or I'm
Mm-hmm.
sorry, the least high frequency absorption, more high frequency reflections. This is less high frequency reflections, and this is even less.
Cool. That's interesting. And
I'm sorry,
Mike,
I'm
oh,
sorry. I had a cranial rectal inversion.
oh no.
This has this has less this has let me just talk about it in absorption. This has more high frequency absorption, so less
Right.
reflection. This has less high frequency absorption, so that it
Got it.
reflects more high frequencies, and this has even less high frequency absorption, so it reflects more high frequencies. Got that?
Is that just the surface area of it all
Yep.
combined with the notches taken out or the lines cut out and stuff? That's really cool. That's interesting.
Yeah,
Mike.
what's really cool. Ted Schultz, a really well-known acoustician, really quantified this. There's a whole bunch of data and equations, but it's basically how big of an area do you have between the perforations for a
Right.
wave to bounce off?
Sure.
So you
Sure.
look at
Sure.
this. This area in reality is about 2 inches. That
Mm-hmm.
means inch and 3/4, something like that. That means that a wave, let's say above 4 kilohertz, is going to bounce off that. Or in this region, it's going to absorb, but so this is going to bounce some energy, reflect some. It's going to scatter some energy. It's a little complex, but you got this in your toolkits.
Awesome. And Mike asks, how does a curved product that you had that has a 3.5 inch at the edge and 5 inches in the middle behave differently than a squared absorber?
Okay, so sorry, let me go back to that. Very good question. So I'll put the blue one, I'll put the red one. So I'm sorry, the 8 centimeters, this is
Mm-hmm.
available in two types, one that's 8 centimeter at the tip and one
Mm-hmm.
that's 12 centimeter at the tip.
Gotcha.
Okay, so it's thicker over here. The curve is the same. The edges are just a little shallower. That's a visual treatment. So the purpose of the curve actually has no acoustical purpose at all. It's only to make the panel look a little skinnier because your eye really catches the thickness of the edge. So when
Got
you
it.
put this in your client's home, they're not going to be as annoyed as if it was a straight square chunk. To
That
be
makes sense.
fair, and to be real, because I don't like fake news. I hate it. This uh, a straight square chunk would work better at low frequencies, as in that energy, that thickness that's lost over here for the sake of aesthetics
Right.
loses a little bit of low frequency. Not that much, if you did a whole room and you could instantly switch them all, you may notice a very slight difference in the articulation in the lower mids.
Right.
Um, but yep, to be fair, there's a little less low frequency absorption out of this for the sake of aesthetics, and it's a known compromise so that we don't have to argue with clients and their designers too much. Very
Sure.
good question. Thank you.
Sure. Makes sense. Yeah. Thanks, Mike. Thanks for the question.
Okay, let's skip over this and let's get into something else. So notes on draperies. Sometimes rooms are going to have a big window and you're going to put draperies. Note that draperies do absorb. They're an
Mm-hmm.
uneven acoustical absorber, uneven in that they may change every day depending on how you open and close the drapery.
Oh, sure.
Um, the performance of the drape is affected by the weight of the fabric, what kind of fabric it is, the pleat, the amount of pleating, and the distance from the boundary. But know that the pleat of the drape that's up against the window or a wall or whatever, that area where the fabric's right up against the window does nothing. The fabric is not absorbing. You really need the air gap behind the fabric for it to work. So
Right.
uh, you need at least a 75 millimeter air gap, which 50 millimeters is 2 inches.
Mm-hmm.
This is 3 inches. So that's the overall air gap. Heavy velour works kind of among the best. You want to have 100% fullness, and you can make the drape out of a combination of absorption and reflective surfaces behind it, behind the actual fascia for some scattering. We make a material like that. We actually, oh, I don't have that in there, but we do make a drape. It's custom made, called Eclipse, where you can just give us the dimension of the drape. We'll make this complex material that is strips of absorption, strips of reflection. It's all curved together, and it gives you a combination of absorption and scattering without too much absorption. So just realize that if you have to drape up a whole right wall because there's a window with a beautiful view of downtown Chicago, that whole wall is going to be all absorptive. And what's that going to do
Right.
to what I've been saying about the absorption amount?
It's yeah, a little too much.
Too much. Mucho, too
Yep.
much. Don't do it.
Dead room.
Um, dead room, not pleasant. Okay, so I'm gonna switch gears from the absorbers and talk about low frequency absorbers, which is sort of just a category of them. Frictional absorbers are just too thick at low frequencies. That's because 100 hertz would require a 10-inch thick material to work, and so we need to switch to other topologies, other tympanic cavity resonators and other ones. So again, frictional absorption works by scrubbing off energy and relies on flow. Diaphragm absorbers rely on pressure, and Helmholtz absorbers do rely on pressure, but they're a resonator. So fluff must be close to a quarter. This is a Floyd Tool slide, but foam, fiberglass, etc. For it to work, it needs to be a quarter of the wavelength you're trying to cover. Here's the different sizes. So 100 hertz has a wavelength of 2.8 feet. It's 0.86 meters. 50 hertz is 5.6 feet. 30 hertz is 9.4 feet. So if you're trying to absorb 100 hertz for some reason, it's got to be really thick. Right. So now, one of the issues for low frequency is we're going to try to treat standing waves, right? In the reflections off a wall, you basically need to treat, again, down to 250 hertz. If you're trying to do audiophile work, again, with fancy high-end cables and all this other stuff, your client deserves to be treating down to 200 hertz, 150 hertz. But the real purpose for low-frequency absorbers is to treat standing waves. So remember that standing waves are the result of a sound wave that's the same size as the room,
right,
or twice the size of the room, or 1.5 times the room, et cetera, et cetera, et cetera. And I'm not going to talk about it anymore because I spent an entire 2 hours last week talking about it.
Yeah, I was about to say we've got hours on standing waves logged by now.
Right. So go look at the webinar from last week, and you'll hear all you want to hear about those kinds of materials. So I am going to say that there are a lot of different absorbers available out there. We make this thing called a deco trap, which is made out of the same dense fiberglass, dense polyester with a wood finish. It's 60 by 60 by 42. It's the 42 is in this dimension. It comes in many finishes. It works from 60 hertz to 500 hertz because it's typically stuck in a corner, and it comes in like all of the finishes you saw earlier. The deco absorbers are also available here, so you can play with those things, put them in the corner of a room, and take care of low frequency absorption, both overall global reflection decay time in the room and standing waves. So we'll talk later about where to put this. Okay,
Anthony, and what I've seen before, because I've seen it both ways. Sometimes I've seen traps like that in the corners that go all the way from the ceiling to the floor, and then sometimes I've seen traps in the corners where it's just like in the middle. Does that depend on room dimensions, or are some people overdoing it by going all the way floor to ceiling?
No, that's a great question. Ideally, this wants to be a treatment from floor to ceiling so that the entire area is quote unquote trapped.
Gotcha.
If this box is open, it's not going to work as well. And what we like to do with this is stack them from floor to ceiling so that the overall resonance character of the tympanic membrane in the front, it's a very damp tympanic membrane because it's on foam. But so that that whole thing takes care of your whole wall. When people are only putting a small amount of it, they may have had budgetary limitations, and at that point you want to put it as close as possible to the trihedral corner. I love that word. So the intersection of the side walls and the floor or the ceiling, and then it works more better than putting it in the middle. Yeah, thanks. That's a good question. So let's switch gears. Let's stop talking about absorbers and let's talk about diffusers. And oh my God, I'm an hour and a quarter into the thing. All right. So like I talked about before, this the way to deal with sound reflections could be some absorption or it could be scattering. The idea of scattering is to break up the sound reflections into smaller pieces so that what hits you is a smaller bullet of sound energy rather than a big, ricochet of a large caliber thing. So let's look at how that gets done. So this is a very schematic version of that thing. The idea is for the reflected energy, rather than bounce off the wall, it gets scattered into small pieces. You're actually preserving the energy in the room, but you are breaking it into more of a smooth mist of sound reflection energy. You can do that by using purpose-built panels, a bookcase, or other broken shapes that ideally would be properly designed. So Um, Now, diffusers are important for getting what's called the overall diffusion character of the room right, and they can also get rid of flutter and slap echoes by redirecting those slaps. So I haven't talked very much about that, but everything I've shown, by the way, is the reflected energy of a speaker off a wall going to the listener. Well, there also are bounces of echoes that go back and forth between left and right and front to back, and those get treated by the absorbers and diffusers we're talking about over here. So diffusers also make absorbers work better because they redirect some of their energy at walls where there's a reflector, but also wall sections where there's an absorber. So an absorber will work better in the presence of diffusers. And overall, they keep some liveness in the room and they fool your ear brain into believing that the room is bigger than it really is. So diffusers are very useful in a room. Again, if you're doing a higher end room for a client that's buying expensive speakers and in which you're supplying high end cables, power conditioners, high end power cords, and all this other stuff, you really should be looking at putting diffusers in there to help support the spaciousness of the room. Okay, so you get a more diffuse sound field. The overall perception of the sound field is just bigger, beautiful, etc. So here's some real measurements of an impulse response. This is a room in which nothing's been taken care of. There's a direct sound coming off the speaker. There's reflections, more reflections, but those gaps, all of that gapped energy just doesn't sound good. If you put some diffusers in the room, you're going to end up, after the sound has traveled from the speaker to your ear, you then receive all of the reflected energy from the diffusers. You see, this is a much smoother thing. This is like sleeping on a nice smooth bed rather than a bunch of rocks. This is sleeping on rocks, and if you're into yoga, that's maybe really good. And hot rocks is even better. But if you're into like a smooth bed, this is what you want. All right. So the idea of a diffuser is it's a surface that's uneven, where the incident sound hits a surface with different shapes and different depths. And you can actually calculate these curves and shapes very scientifically so that the re-reflection is completely smooth. You want a good diffuser to have a return into the room that scatters the energy very evenly, just like a Lambertian screen for video. It has an even distribution. The depth of this material is going to determine how low of a frequency the material works to. A very thin material is going to work for short wavelengths. A thicker material or a deeper material is going to work to longer wavelengths. So ideally, the scattering surfaces are, about 8 inches, 20 centimeters. If you really want good sound, and if you want superb sound, you want to go as thick as 12 inches. So that's a pretty big material on the wall. In reality, in the real world, it's going to be hard to convince people to do that, but you need to always know what's the ideal. So know that when you're going into a room, if you want really good sound, what's going to be put on the wall is 4 or 6 inch absorbers and diffusers that are 6 to 8 and preferably even 12 inches deep, which is 30 centimeters for you people listening outside of the US. All right, so in order to understand that, there's an interesting thing about the scattering bandwidth. So note that it's not just as easy as how deep the diffuser is. Let's look at this. If you take a pole that's 20 centimeters in diameter, so that's 8 inches, and you send sound to it that's 100 hertz, which has a 3 meter wavelength. This is 0.2 meters. This is 3 meters, also known as 10 feet. That 20 centimeter pole is going to be ignored by the waves. It's just going to wrap right around it. Okay, it's like driving over a penny with your car. You're not even going to know that it's there. If you throw a sound at that pole, again, it's an 8 inch pole, 20 centimeters. If you throw a 10 kilohertz sound, which is 3 centimeters, which is about an inch, a little bit more, actually an inch and a half, a 8 inch pole, the sound's actually going to reflect off it. It's not going to scatter. It's actually going to bounce off the pole. Depending on where it's hitting, it's going to bounce it off different places, but it's not going to diffuse. It's just going to bounce off. If you take a 1 kilohertz sound that has a 30 centimeter wavelength, which is 1 foot off an 8 inch pole, it's going to scatter off it because the wave is about the same size as the pole, and the sound that's going to hit that is actually going to scatter evenly in all directions. So that would be like going back to the car analogy, if you're going to drive over a penny with your car, you won't even know it's there. If
Mm-hmm.
you drive over a 4-foot tall block of concrete,
Yeah. You might notice, you might feel that one.
if you don't drive too fast, you may actually reflect off it if you hit
Yeah,
straight on
yeah,
with your
yeah.
bumper.
Um,
Um,
it's
and if
funny
you,
it's funny you're using this analogy right now because there's a music venue that I frequent, and there's this big giant structural pole for the building, like right in the middle of the floor where you're standing there and trying to watch the band. And I've always wondered if that big giant pole in the middle of the floor had any effect on the acoustics, and it sounds like it does.
it probably does a little bit. If
Sure.
it's a lonely pole, it probably has, in a bigger venture,
Yeah.
a bigger venue, it probably doesn't have a very big global effect. But
Yeah.
hey, maybe you can stand closer to the pole and get some
There
scattered
you go.
energy off.
Yeah, these are
Um,
the kind of things that go through my mind in between bands or, waiting for the, it's just like, I wonder if that pole up
geek,
there is changing. Yeah, yeah, yeah.
geek.
Hey man, it's in my blood, it's in my DNA. I can't help it. Can't help it.
Um, so now imagine with your car that you're driving past this happened to me. You're driving past a pole that's say 6 inches, but it's not that tall, so you don't even know it's there. Now you've actually scattered your car over the pole
Mm-hmm.
because you've dented it, you've broken it in two. So
Right.
you do have to understand that different size materials work at different frequencies. So um, I am going to pass this so that we have a little bit more time. So let's get into what's called engineered surfaces by Floyd over here. So there are purpose-made panels in which there's very careful arrangement of the different surfaces. They sometimes look like this. This
Mm-hmm.
could look like a diffuser made by a few different companies. They're made so that the sound that bounces around in these different surfaces is scattered very, very evenly in a very even distribution. And that's sometimes known as a scattering coefficient, sometimes known as a diffusion coefficient, depending on which part of that you're looking at. But ideally, a good diffuser is built in a way that it scatters the sound very evenly. Now, you can make diffusers out of what's called either cylindrical surfaces, like the pole
Mm-hmm.
you're talking about, which are really going to have an effect centered over one range of frequencies, or polycylindrical, in which as you see here, it's a constantly changing radius. So this is a small radius, bigger radius, bigger radius, bigger radius. And those things tend to have a scattering character that is also broader band, not as smooth and as even as that, but they have
Mm-hmm.
their spaces. So these work very well in performance spaces. You'll see them a lot in studios, and there's places for these. So
Right.
if you are going to use semi-cylinders or polycylinders, they can work pretty well. Here's the actual data from Peter D'Antonio and Trevor Fox in a really good book called Acoustic Absorbers and Diffusers, that actually shows the normalized diffusion coefficient of something like that. So that can actually work pretty well over a range of frequencies. You can see here that depending on the angle and the type, you're going to get different absorption or diffusion coefficients. If you do use those, space them apart. Do not place them side by side. Sometimes I see rooms in which there's a cylinder or a semi-cylinder, another one, another one, another one. That doesn't work. That ends up becoming a reflector. Give a gap between them. So um, in terms of scattering, overall, you want enough of these scattering surfaces to smooth out the sound field. They really want to be thick, between 15 and 30 centimeters, which is 6 to 12 inches, or else they don't work quite as well. And you want to balance how much absorption and how much scattering you have and interleave them. So I mentioned that before in the section on absorption. You want to mix the scattering devices together with the absorbers. It is the stuff that high-end studios and high-end recording and high-end listening rooms should be made of, okay? So there's a lot of different scattering processes, a lot of different math. There's a thing called a quadratic residue. There's a maximum length sequence in the calculation of it. There's a primitive room calculation. There's a whole bunch of different ways to design them. I would go look at this resource over here. It's a really cool one. Ultimately, just in very quick senses, these QRD diffusers have been around for, wow, going almost close to 40 years now. They have a predicted very smooth character. They can be frequency selective. They can vary in bandwidth and smoothness depending on the type. But warning, if you put a lot of them and you're close to them in a room that's kind of small, they can end up with sort of a zippery sound because the reflective or the scattering character has a sequence, and you hear that
Oh,
sequence.
yep.
So I've been in recording studios where they just went crazy with them and put them everywhere. And everything just sounded coming off the speaker like it was like zing, 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 not pleasant. Yep. So don't do that. Overall, you want a uneven surface. You want surfaces that are as broken as possible, that have an even polar pattern and as smooth as possible. So let's look at how these QRDs work, just to be clear. An impinging sound will hit it, and over a range of frequency, which is based on the depth of this, there is a resonance based on that depth, and at that resonance, the sound's going to scatter out into small pieces right off that edge over here. At a different frequency, it's not going to do that. It's not going to resonate, but at a different frequency, you have a different well depth over here, and a different frequency, you have a different well depth. So these things are built with wells at different depths so that those diffusion effects happen over a range of frequencies. That's why they have these different depths. So those diffusers, all diffusers can be quantified. There is a thing called the diffusion coefficient and a thing called the scattering coefficient. There's a very good paper you can download. There's a spec from the Audio Engineering Society that explains that. Very loosely or very softly putting, I'll say that the scattering coefficient shows how much of the incident energy is scattered. So given a direct sound that reflects off a hard surface, which would have a zero absorption or zero scattering coefficient, a perfect diffuser would have a diffusion coefficient of a scattering coefficient of 1. But in addition to that, there's this other thing called the diffusion coefficient, which shows the uniformity of the scattering. So there's a way to build a diffuser that's scattering all the energy. There's no reflected energy compared to a hard wall. It's all putting it out everywhere else, but it could be uneven. So what you want is you want both the sound to be scattered evenly, and you want it to be uniform. This is just like, again, a screen surface. You want it to be Lambertian if the room is dark, which is you want it to illuminate in all directions evenly. All right, here is a measurement from a venerable product in the industry called this is a company called RPG. They make the QRD 734. This thing's about 40 years old, I think now.
Wow.
And this shows, it's been around for a while. And this shows the diffusion coefficient, and it shows the scattering coefficient. So this has a very good scattering coefficient up to about 0.8. 1 would be perfect, but basically unachievable. And so it starts at about 600 hertz. It's a deep box. Starts at 600 hertz, goes up and down a little bit, and this shows the evenness of it. So it's not perfectly even, but pretty damn good. Note that this also absorbs a bit of sound, not very much, about 0.2. So this is data that you should be looking for from manufacturers, okay? There's other forms of diffusers like the RPG, bicubics, and waveforms that are newer technology and newer topologies. The absorption, the diffusion and the scattering character is smoother. Here's what the responses are over here. Remember those notches, those peaks and dips that you saw in the QRD? That's largely resolved in these new shapes that Peter D'Antonio from RPG has been designing. So you'll look at most of the newer stuff from them. They've gone away from those slots and more into these kinds of curved shapes. So
Anthony, when this stuff is measured, I'm just imagining this, and I could be way off here, so you can probably clarify it for me. So I'm imagining that they're putting one of these panels in like an anechoic chamber and just blasting sound at it and taking measurements. Is that how they're measuring the coefficients and coming up with some of the numbers?
So that's one way to do it. And what you do is you measure it anechoically with what's called a goniometer, which is a array of 20 microphones. I may have a picture coming up here. I don't know if I erased it off the presentation so that it wasn't a 4-hour presentation. But yeah, you measure it at you can measure what's actually does in an anechoic space, you first put a hard surface, you look at the reflection off that hard surface from a number of microphone positions, and then you put the device under measurement, you measure again. That's one way to do it. There's other more sophisticated ways to do it in actually in reverberation chambers with a rotating turntable where you're looking at the effects of the reflection from the devices. And actually the most accurate way to get it, all of those actually have some measurement idiosyncrasies. The most accurate way to do it is to do a mathematical model of the thing using a few different topologies. So on a computer, you can actually model the effect a whole lot better, and that's the right way to do it these days.
Gotcha. Cool. Thanks.
So now, generally, I'm going to group diffusers into 2D and 3D diffusers. I've already talked about this a little bit before. I am using the term 2D to represent that the sound that's incident is redistributed in a hemi-disc plane, which is like half of a disc. Okay, so it's a flat surface, not just a single vector, but a flat surface. I'm not using the mathematical coefficient of the quadratic residue equation. I'm just representing this as a geometric space. So there's 2D diffusers and 3D diffusers that redistribute the sound into a hemisphere. And I like to use 2D diffusers towards the front of the room so that the energy is diffused only horizontally. And I like to use 3D diffusers towards the back of the room so that the sound is more hemispherical. It's more like it is in a concert hall, and it supports the surround speakers a whole lot better. So here's examples of 2D diffusers. The sound that hits the cylindrical shape is going to re-radiate out horizontally. If you turn it this way. If you turn it the other way, it's going to radiate vertically, which you should not do. And here's one of many different slotted diffusers, whether it's security or other devices. Same thing happens over here where the sound re-radiates out only in a plane, okay? That's a 2D diffuser. Conceptually, a 3D diffuser could be a shape like this. This is a diffuser made by the company called ART that's redistributed. Very difficult with by the way, with PowerPoint to create a hemisphere shape.
Oh, sure.
But the same thing would happen off a pyramid, which is not a very even diffuser, but it does break up the sound into 4 main directions, or this box or that box. These are all what I call 3D diffusers. These are also RPT products. This is a 2D diffuser, scatters only horizontally. This is a 3D diffuser, scatters horizontally and vertically. If you put it this way, if it's on the ceiling, of course, it wouldn't be horizontal and vertical. It's just this scatters in one plane, this scatters into a hemisphere.
Sure.
All right. So bunch of products, other products you can get. So we make this thing called Dimension 4 C-Fuser, which is a beautiful wood box that's a cylinder that scatters in hemi-disc. It's deep, so it works from 400 hertz to 2 kilohertz, 15 centimeters deep. We also made it into a bass absorber. So the internal volume of the box is used to trap some low frequency, so it does dual duty. Made out of wood, really pretty, a little expensive, but it's gorgeous. We also make what we call the P-Fuser, which is 4 pyramids arrayed together in a really kind of nice look. It's a P-Fuser pyramid, quadri pyramid, 15 centimeters deep. It also has slots over here, works as a bass absorber. You would use this, again, in the back half of a room in the ceiling. Under the Sonatus line, we also have what's called a 6 strip, which is a 2D diffuser with an absorber core in the middle. It works, actually that is wrong. That's the absorption works in that range. The diffusion works from 2 kilohertz on up. We also have this thing called a 4-fuser, which is very cost effective. It's actually hard expanded polystyrene with an acrylic coating on it. Very, very low cost, works pretty well. It's 3.5 inches deep. And then we also have a thing called a big fuser, which is a 3D diffuser that's 60 by 60 by 15 centimeters. That's 6 inches deep, works down to 300 hertz, very cost effective. I think it's $37 if I remember right, which is about as cheap as it gets to get a 3D diffuser.
Yeah. What do these things weigh, Anthony, when you go to mount these? Are they requiring big wall anchors, or are they pretty light?
Very good question. This thing's only about 3 or 4 pounds.
Oh,
Again,
sweet.
It's polystyrene. It's a
Yeah.
hard polystyrene that's actually finished with an acrylic coat. It's a hard material. You can this particular model you can get in any color as long as it's black, white, or gray.
Yeah, it comes in anything
Um,
as long as you
and,
can.
and because it's very lightweight, actually, we offer a mounting kit that's actually 4 little magnets that you put onto the
Oh,
wall,
great.
and then you mount some small metal plates on the thing, and it just goes click.
Very cool.
So again, you use those towards the back half of the room and the back of the ceiling. I see people putting these things behind a speaker on the front wall. Bad idea, not useful. I
Yeah,
see
doesn't
people
sound
putting
right.
those at the first reflection. Not a good idea. If you put those at
Hmm.
the first reflection, the sound that hits those, some of it's going to get scattered horizontally. Some of it's going to go
Right.
up to the ceiling
Yeah.
and bounce back to you from the ceiling and narrow down the sound field. Not good. Um, Now we also make so this is called a big fuser. We also make the big fuser massive,
The
massive,
massive edition.
massive. So you asked about how much that weighs. This thing's uh, this thing's about 35 pounds, 35,
Gotcha.
probably 40 pounds. It's
Hmm.
heavy, and it's heavy because it's made out of solid wood.
It's solid
It's
wood, yeah.
18 centimeters deep, which is 7 inches deep, works down to 270 hertz. Works really good, beautiful. Um, Expensive. I think it's about $260 if you call that
Hmm.
expensive. If you're doing I'm going to keep saying this thing. If you're doing an audiophile room in which you're worrying about the kind of cables and power cords, your
Right.
client deserves this
This
stuff
is
on
the
their
right one.
walls.
Sure.
This is the right thing to do. Now, you may
Hmm.
hide it behind stretch fabric where you're going to be really careful about the fabric, or it's pretty enough that you can put them around the room and it's going to, look like a modern art sculpture.
Right.
All right. So, quick summary of all of this. Sound reflections can degrade the sound quality and sound staging. The reflections can be detected with mirrors and pink noise. I haven't talked about the mirrors.
Yeah, the mirror trick's
Uh,
cool.
yeah, mirror trick, real quick. If you want to know where first reflections are, you can walk around the room. You can sit at the main seating location, and you can have a person walk up and down the wall with a big full height mirror wherever you see the mirror as a first reflection. That
Hmm.
may or may not be a place where you want to treat the sound. So I don't really talk about that too much, but if you want to know where the first reflections are, that's a good way to do it. And the treatments for that are absorption and diffusion. Now,
Right.
finally, in the last 20 minutes, like I always do, I keep the best for last. Let's take all this info and let's design a room. So
Excellent.
first off,
And
how,
I'm sorry, Anthony. Real quick, just because Mike had a question, I don't want it to get lost. When you talk about putting bass absorbers in the corners, he says if they help even out the bass response in the room by slowing down that energy, do they also slow down any bass energy that would get transmitted through the wall?
Very good question. No, they do, but so little it's not even answering the question. Or I'll answer it. The long answer is very, very, very little,
Hmm.
very little. However, and it's always complicated. I wish the science was more direct, like mac and cheese. Although mac and cheese, you could say is a complicated science.
Yeah, it's
Um,
a lot of chemicals in there.
so here's the if and or but. If a room has a lot of standing waves, which means that the energy is bouncing around the room and resonating, I talked about this last week, and you
Hmm.
put good bass absorbers in the room that get rid of the resonance, well, that resonance is now not pressuring the walls. And so you've reduced the amount of standing wave energy, which means that the walls are less excited, which means there's a little less energy going to the neighboring
Sure.
rooms. But a
Good.
regular absorber that's doing, free field, free flow absorption anywhere around the room, by the way, is
Hmm.
not really doing anything for sound ISO. So I should point that out. Um, Everything I'm talking about over here is about treating the inside of a room
Right.
and does nothing for sound isolation or for sound, I would say, for sound privacy to neighboring spaces.
Got it.
Um, I said nothing. It's going to affect at a half a dB or 1 dB. Not worth talking about.
Hmm.
So thanks for bringing that up.
Yeah. Good. Good.
Okay, so how much do we put in there? Remember that you want some reflections in the room. You don't want them all. You want the right amount. So the amount of decay time and spectrum have to be just right. Depending on the size of the room, the amount of time is short or long. You want the decay of an impulse response to look like this. The decay time should be between zero point 0.2 and zero point 0.4 seconds. And research shows that most people like about the same range of time given a certain room size. I think I talked about this several sessions ago. There's some really seminal work done by researchers going on 35 years ago that shows that most people like a decay time that's about the same given the room volume. So some people like a little bit longer, some people like a little shorter, which is, which that time just tells you how much reverberation is in the room or reflection there is. But this is the equation that you can use to determine, given the size of a room or the cubic volume of the room, how much decay time you should have. So now the decay time hey, I noticed that same thing over here. Sorry, let me fix this.
No, go for it.
Yep. So you've seen it here live and in person.
And there you go.
So given the size of a room and square footage, which I'm relating back to cubic footage by assuming certain ceiling heights, these are the reflection decay times. Okay, so on average, it's somewhere in this range over here. So a 300 or 400 square foot room, which is most of the sizes we're doing, the decay time should be somewhere around 0.3 seconds. Now, that decay, how the energy falls off with time, should be ideally the same at all frequencies, with some tolerance. So you can actually tolerate a longer reflection decay time at low frequency, up to 2 times longer, which is a fair amount of tolerance. And then at the higher frequencies, you don't want the decay time to drop off suddenly, but above 4 kilohertz, you can tolerate up to half the decay time. So if the target was 0.3 seconds, you can actually tolerate 0.15 without going, wow, this sound sucks. Ideally, you want the decay time to be as even as possible with frequency. Most rooms are going to have enough trappings that are going to naturally drop off the high frequency, which is why our highest end panels don't absorb as much high frequency as they do absorb mid frequencies. Okay, so let's go over here. To figure out how much you need in the room, you can actually predict what the amount of absorption you're going to put in the room is going to do by this decay time. So this is what's called the Sabine equation. This is what's called the Eyring equation. And this is what's called the Arau-Puchades equation, which is from about 25 years ago. And this is what you want to calculate given the volume of a room and the absorption coefficient of the materials you're using on the 3 axes, the length, width, and height of the room. This is a really complicated calculation.
Sure.
For every room you design, you're going to have to calculate this. Or I'm going to wait until my audio connection reconnects. Can you still hear me?
Yeah, you sound great. You got me back, Anthony? Oop. I had him just fine, and it sounds like we may have just lost him. Oh, there he goes.
I'm back. Okay.
Yeah, I only lost you for a second or two. You're good.
Yeah. All right. So you saw all those equations, right? So ideally, this is the most accurate calculation that tells you how many square feet or square meters of absorption you need to use in the room. This is a royal pain, or you can just use this guideline, right? This reminds me of.
That seems a little easier.
It's a little easier. So there's a lot of areas of science where you study all the really complicated thermodynamics of it, and in the end you end up with a chart that goes, the answer is 2. So this is the guideline. 15% of the wall surfaces are absorbers, 20% are diffusers. You spread the absorbers around the room, you interleave the absorption and diffuser. Asymmetrical layouts are better. So let's, don't forget to treat the ceiling, and there you go. All right, now let me go to the diagrams.
You know what that reminds me of, all the equations, what you had said just a moment ago. It's like in video when we study 2-3 pull down.
Yeah.
The math behind it is crazy, and there's a reason why it was such good technology. But at the end of the day, we just want to know where it's at in the menu and how to turn it on.
Exactly.
The math behind it's just too crazy.
So this is a classic case of people just wanting you to know how to fish rather than go, here's a fish, go eat. And so I've taught you guys how to fish in the last 2 hours. Now, here's the fish, okay?
Right.
So this is the acoustics recipe of everything I just described. I already showed this diagram earlier. This is, if you lay out a room like this, where you put some absorbers and diffusers on the walls with 2D diffusers towards the front. I can see that my audio connection has been lost, so I'm going to wait a little bit.
I've got you back. Oop. Anthony, we may have lost you. I don't have any audio from you. Stand by, guys. I'm sorry about this. Guys, sounds like we just have like a tiny audio issue here. And, ooh, guys, we may have lost Anthony altogether. So stand by, and hopefully we didn't lose his connection totally. You can still see his screen just fine, but I've lost audio. Guys, if you could just be patient for just a moment, and we'll try to get.
I am back.
Oh, there he is. Okay, guys, all good, all good. Crisis averted. Crisis averted.
Streaming live to you from very far away.
Yeah,
Okay.
this is one of the beauties of doing it live.
It is. It is. Okay. So lay out some absorbers in the room, not everywhere. Lay out some diffusers in the room, some 2D towards the front, some 3D towards the back, and lay it out this way. So this is the left wall. Here's our speaker behind an acoustically transparent screen. On this left wall, I'm first going to put some 2D diffuser. So not absorb the first point, but actually scatter it. Then I'm going to put an absorber. I'm going to put some diffusers, an absorber, some diffusers, and absorber. This is 2D. That's 3D diffusion.
Yep.
Now, that looks like a lot of treatment, but if you actually take those absorbers off the wall and put them all in a corner, look at how much of the room I've treated. This is half of the height, and that would be half of the width. It's less than 25%. It's more like that 15 to 20%.
20, yeah.
Right? So that's 3 absorbers. In this case, I'm using 2x4 foot panels, which are commonly available. A bunch of diffusers, 2x2 panels, and that's how I would treat a room like this. Okay. The right wall would be absorber, diffuser, absorber, diffuser, absorber. Here we're putting 4 absorbers on the walls. It's a little bit more on the right wall than the left wall. And then we're putting some 2D diffusers and 3D diffusers interleaved. 2D towards the front, 3D towards the back.
Right.
So somebody out there is probably going, wait a minute, that looks totally different to this. This is the left wall, that's the right wall. Yes, it does. The pattern on the 2 walls really is best put laid out in a slightly different way, to where what's off the right wall is a slightly different pattern in terms of scattering and absorption than the left wall. And I know that sounds totally counterintuitive, but actually it provides a lower the real term is a lower interaural cross correlation. It provides more asymmetry in the character of the reflections, and your brain likes that better. It just sounds better. I talked about this in a session several weeks ago, so you can go back and refer to that. Okay. The back wall, it's good to put absorption in the middle of the back wall to stop the sound energy that's going between the front and back wall, and some scattering devices, some 3D scattering devices to the outside, maybe a 2D diffuser up there. Okay. Now, what does that all do? The direct sound's going to hit you. The reflected sound, some of it's going to get absorbed, some of it's going to get scattered, some of it's going to get reflected off the areas above and below the panels. Sound is going to get absorbed, scattered, absorbed, scattered, absorbed, scattered. So what you get in the end is still some scattered and reflected energy coming back to you in a smooth way, rather than these hard pokes of reflected energy. It's a smoothed out and orderly sound field, so that in the end you end up with this, again, like I showed it earlier, this crescent of sound energy that surrounds you. That's what you want to try to get.
It's like petting your dog versus slapping it. It seems like.
I never used that before, but
nice,
okay,
smooth,
I see that.
a nice, smooth, even thing rather than just pop. You know.
Yeah.
I don't know if that makes any sense or not. That was just the first thing that came to my head.
I like that. I like that. No, it's like mashed potatoes, where you have a lot of chunks in it versus really smoothed out. How's that?
There you go. There you go. There you go. I like that too. I like that too.
Yeah. Anyway, I'm getting hungry. I guess it's getting close
to
lunch.
To say, I haven't had lunch yet, so be careful on the food analogies.
So when a room is properly done, you're going to get a direct sound. You're going to get a nice, even distribution of reflected energy. It's not deadened out. There's still some reflected energy. It's going to last between 0.3 and 0.4 seconds before it reaches its diffuse field and dies out 60 dB. That's known as the RT60. That's what you want to try to get. All right, let's look at some layout schemes. So everything I just showed there is, little diagrams in PowerPoint. Let's actually look at things you can go out and get and make it look like. So this is a room rendering off a room that's treated with our standard Sonatus system. There's a low frequency absorber, using the Decozorber in front. There's a corner trap over here, which one of the people asked. Ideally, that does want to be on the floor, and ideally, you want to do a whole column of it.
Right.
This over here is a diffuser. That's an absorber. That's a diffuser. That's an absorber. Okay. There's a higher end solution called a premium. Here's an absorber. Here's a 2D scattering diffuser, absorber, 3D diffuser. Remember, this is the, like the quintessential picture. Try to absorb at spread areas through the room.
Right.
Put 2D diffusion towards the front, 3D diffusion towards the back. On the ceiling, absorb towards the front of the ceiling. I went over that really too quickly earlier, but really absorb towards the front of the room where that first reflection would otherwise bounce at your head, and then diffuse the back of the room with 3D diffusers.
Right.
And these could be these guys that weigh just 2 or 3 pounds, made out of hardened styrofoam.
Very cool.
This is our ultra solution, the expensive one, where the absorbers are thicker, the diffusers are all made out of beautiful wood. That's what it would look like. And here you have absorption, corner absorption all the way up and down.
Sure.
So again, absorber interleaved in the room, 2D diffuser over here, 3D diffuser towards the back. Okay, these are diagrams that show the different packages. So we make packages for a 250 square foot room. For a 350 square foot room, there's just more treatments. For a 650 square foot room, just more treatments, but it is always the same guideline: 15% absorption, 20% diffusion.
Sure.
Our ultra line called Sonatus Ultra. I'm sorry, this is the wrong thing. So this is Sonatus Premium, absorber, diffuser, all the way around the room. Cluster the absorbers a little bit in the middle of the back wall, because that reduces the energy going back and forth. And that's for a 650 square foot room. Just more of the material, just still interleaved around the room. 2D diffusers towards the front, 3D diffusers towards the back.
Anthony, do you, like, when you walk into a room, let's just use a 2-channel room, for example, when you walk into what potentially is going to be a 2-channel room, because this happens to me sometimes, I'll look at the room before the room's even been worked on yet. It's just we're speccing it out at this point, and the room will be like perfect shape and size. And in the back of my head, I'm going, okay, great, I can work with this. This is going to be awesome. Do you kind of get those same feelings as well when you see a room for the first time? If it's like, and what triggers that? Is it if the room's on the smaller side, on the bigger side? Do you have anything that kind of gauges you there? Or can you spot a good room just by standing in it?
Well, so yes, a lot of the rooms I work on are actually on plan, so I get to see the ratios and the
that's
character
excellent
beforehand,
and
I can
awesome.
look at that, and I can calculate it and model it and go, this is going to work or this is not going to work. If a room is long and narrow, it's going to be really hard to get really good sound and picture in it. If it's kind of a ratio of about 1.2 to 1.3, it's going to work better. It's more squarish. Everything works better. The walls aren't too close to you. There's a little more distance between you and the walls. However, it's hard to just look at a room and know if the standing waves are going to be good or bad. And that you have to measure or play low frequency in them to figure it out. So that's the domain of that conversation from last week.
Yeah, there's been times where friends of mine have said, like, hey, can you come check out my room and see if this is appropriate for a theater room? And I'll take one step in the room and I'll be like, nope, ain't gonna happen. Or in some rooms, you're like, oh, dude, this is perfect. You've got a blank canvas here. This is great. I just was wondering if you ran into that too.
So after doing 1,000 rooms, I got to tell you, I've been in spaces where I thought they would work great, and in the end, the results were not amazing.
Oh, interesting.
And I've been in rooms and you go, God, this is not going to work. And you just go, well, that's what I got. The client says, make it work. And you make it work. And it's like, oh my God, this sounds amazing. I've been fooled. It's complicated.
That's cool. I like that.
Like the title of one of my favorite movies. It's complicated. It's about as complicated as relationships between people. I love that movie. It's a great movie.
There you go.
Okay, so the Sonatus Ultra 350 looks like this for a room that's 350 square foot. For 650 square foot rooms, looks like that. More absorbers, more diffusers, but never too much. Okay.
Right.
This is a kind of a more 3D rendering. All right, in our higher end line, Dimension 4, we have also different solutions with absorbers and diffusers. Again, here there's systems for smaller rooms, bigger rooms. I'm not going to spend too much time on that. That I want to stop at. So this stuff on the wall is generally ugly. you
Mm-hmm.
generally want to cover it with stretch fabric. So
Right.
um, you look through the catalog of all of the CEDIA award-winning rooms, and the majority of them are rooms that are actually stretch fabric. They have
Right.
upholstery. What's hiding behind the upholstery is this stuff.
Sure.
Okay, absorbers, diffusers, subwoofers, et cetera, et cetera. But you
Mm-hmm.
definitely want to hide it. The look can be just about anything you want. It can be sheer fabric from floor to ceiling, front to back. It can be
Mm-hmm.
interleaved with pilasters. It can be interleaved with chair rail, whatever you want. Doesn't really
Right.
matter. Just that it's dark and neutral for video, and you can do
Yes. Yeah. Thanks
that.
for mentioning that too.
So we also make this line called Concerto, which is main role is to, this is for the client that says, I'm not doing an acoustically transparent fabric,
Mm-hmm.
but we make these panels that actually can be put on the wall. They're thick in the middle and they taper down to very thin, and it's hard to see in this picture, but if you choose a blue panel and you put it in a blue room, or a gray panel, put it in a gray room, they tend to kind of
It'll melt
meld
in.
into the background,
Yeah.
and you just don't
Yeah. That's
really
cool.
notice it. So here's a listening room with some high-end gear,
Ooh, it's a nice
older
listening
room.
room.
Yeah, two different colors. And we also make this higher end solution called Symphony, in which there's, I think I showed the individual components of that. This is another, this is actually a high-end showroom with a Symphony
Yep.
system. So you can make these things blend in. This is a recording studio with a Symphony system where
Mm-hmm.
it was not needed to be blended in. In fact, it's blue with yellow. It's like totally poking out. This
Yeah.
is a high-end listening room uh,
Nice.
for actually, these are really expensive speakers and all this stuff. This room sounds unbelievable.
Oh yeah.
Um, and yep, it looks techy on the wall, but this is what you do for a client that's going to spend all the money on really expensive electronics, expensive wires, expensive everything. So
See, I like that. I like. I know. I've seen those CEDIA awarding systems before, and I do appreciate that real clean look of being behind the acoustic materials and stuff. But man, I'll tell you, man, I just personal preference. I love the way it looks when it's exposed, like what you're showing right now. I think that is
right,
so cool.
it's because you're a geek.
I'm a nerd. I know. I can't help it. Um, there was a question that came in, and I think you may have actually touched on this, Anthony. But Robert asks, when you go back and look at some of those rooms that you had the diagrams for with the guy in the red hat, how do you determine the spacing on the side walls for the absorber and then the diffuser? So I know the
Mm,
general rules, 10%, or I'm sorry, 15 or 20%, depending on what you're doing. But like, if you're going to do a panel here, a panel here, a panel here, how do you know how much to space them out? Or
yeah,
what you showed before is they were spaced out nice and evenly, but then you also showed them all kind of together at the back of the room. So is there really a
right.
rhyme or reason on that?
Yeah, that's a great question, and that's another hour conversation. So typically, by the time you're going to have that 15% of absorption, 15% of diffusion, it is kind of going to fill in the walls, kind of like you see here. I know this
Yeah.
looks like a lot of stuff, but if you took all of those absorbers and you cluster them all into the corner, it's not a big portion of it. So this is probably a good picture. So this zone right here is left kind of open in this room.
Hmm.
You'll notice that they're generally oriented in the zone between the speaker and the back of the wall. And there's gaps of about 4 or 5 inches, maybe up to 6 inches between the things. So the real key is lay out the absorbers as evenly distributed as possible. Fill
Hmm.
in with the diffusers. Make sure that there are not gaps that are much bigger than 6 to 8 inches between them,
Right.
and you'll be fine.
Sure.
Um, and you can get a lot more scientific and a lot more complex about that, and that's the domain of what we do when we charge, $15,000 when we're engineering a room. That
Oh, sure.
$15,000 goes into tons and tons of math and tons
Oh,
of,
of course.
finite element analysis and all this other, crazy, very complicated computer modeling.
Sure.
And that's the domain of people who are spending lots of money on really good audio.
Hmm. Good. Michael asks, he says, in the side view diagram of, okay, yeah, in the side view diagram of absorption and diffusion, it looks like those are all treating the left, center, right channels based on height. If your rear speakers are higher up, would the rear channels
Yeah,
also need treatment?
yeah, that's a good question. So um, the ideally, you really want to think of the front channels as the most important ones. I think we've talked about that in some other places, but the most important speaker is the center speaker. That's carrying like lots. If you look at the net energy over time, the left and right speakers carry 3 dB less energy than the center. The sides carry 3 dB less. The back carry 3 dB less. And the tops are gone. Overall in the net energy in the room. So most important speaker is the center one, followed by the left and rights, and that's where you want to put your attention. And yes, if you have a tallish room and you've got surround speakers that are up in there, you don't want them to be in a place with really strong echoes, and you do want to do some treatment. For the sake of simplification, I've shown concepts. If I can get to it, I'm going to show you a bunch of actual in-room designs we've done, and that's going to answer your question. What do you do further up to make sure the surrounds work? So
Cool.
We're at 2 hours, and if you guys are willing to spend another 10 minutes, I'm just going to flip through a whole bunch of diagrams.
Yeah, sure.
Do we have
Let's do
anybody
it.
left?
Oh
Is
yeah,
there anybody left?
everybody. Christian dropped off, but everybody else is still here. We're good.
Bye, Christian.
Yeah,
Everybody else, thank you so much. So yeah, I'll make your next 10, 15 minutes be totally worth it. Ready? Go. So, yeah, is there another question?
No, I was just going to say that bringing up kind of to piggyback on your point about the center channel, I've just heard over the years the general consensus has been that your center channel is like 75% of the movie. Is that 75% rule? Was that just some wives' tale, or is there something to that?
No, that's true. That's
Yeah,
true. I mean,
that's what I always thought.
there are scenes in which all the sound's coming out of the left speaker, so it's not like the left speaker never does anything.
Right,
But
right.
if you looked at the total energy over the time of the total time of the movie, like if you could actually measure the average, you'll find that the center has 70 to 75% of the energy. Yeah.
Right.
So, all right, here's a bunch of great reading material if you guys want to learn more about this. This is a great book, the Master Handbook of Acoustics by Alton Everest.
I have that one.
Hey, yeah, I named my first my first son Alton for that.
That's awesome.
It's Alessandro Alton. Other reasons too. This in Old English. Okay, off acoustics for a second. I love digressions. This is the first digression of the day. It comes from Old English, means all sort of all town, all old area, and it just means somebody who's wise.
Oh, that's cool.
Anyway, so F. Alton Everest was a very wise guy, wrote some really, really good books on acoustics. And there's a bunch of other great resources. There you go. There's other ones over here.
Guys, screenshot those, and I'll tell you. Anthony had mentioned.
Oh my goodness! Oh my goodness! I know why that's here. Okay, go ahead.
No, I was just going to say the book that's on your page right now, the Acoustic Absorbers and Diffusers Theory. I did look that up a little bit earlier, and it is available on Amazon. It's out there, and a few of these other books are pretty easy to find as well. So, guys, as Anthony's showing you these resources and these different books, maybe screenshot that if you want to take a look at those a little bit later.
All right, or you can see it. So I totally forgot Floyd Toole's book in this presentation. He's gone through a few different editions called Sound Reproduction by Floyd Toole.
Right.
Very, very good book. It's pretty thick, and is going to talk, of course, about this, but a lot of other things too. So,
sure.
A good resource. All right, so let's forget all this. This is how you can reach me. Screenshot that if you need to. Actually, if you either need to hire us to help design a room, or if you need to reach me to ask any questions, either do it through AV Pro or you can email me directly. I'd rather you actually went through AV Pro for questions so that they can be redistributed to other people.
Yeah, that's a good point, guys. If you have any specific questions for Anthony, send them to me, because then we can take all those questions and compile them together, put them on the Meridio forum so everybody can see them. So that's a good point. Thanks for calling that out.
All right, so now what I've got is a compilation of lots and lots of different rooms. Oh my God, there's 200 pages over here. I promise I won't show them all. No way. But yeah, I've got a whole bunch of different rooms that we've done that help show kind of how we've dealt with it, and including, well, where do you put these things when there's surround speakers? So this is a recording studio in New York City that does award-winning movies. It's fully Atmos compatible, yada, 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 yada. This is where we put things. So this is the layout of speakers. There's 4 pairs of Atmos speakers over here. And these are the various treatments on the walls, different types of absorbers and diffusers, and I'll just show you where everything goes. This is what I call the peeled out view that shows the ceiling, the right wall, the left wall, the front wall, and the back wall. And I'm going to show you each wall individually. So this is what's on the left wall of this room. So this is a professional mix environment for Atmos applications. There's a front speaker, happens to be our Grimani Systems, the larger one of our speakers called the Alpha. And there is an array of surround speakers, which is more than you're typically going to put in a home cinema. But remember, this is a film mixing room. So absorber with a diffuser above it, diffuser with an absorber about it, absorber, diffusers with an absorber above it. This is also an absorber. Here's another absorber. This one's a little skinnier, so you can walk around the wall over here. Absorber, diffusers, absorber, diffusers, and you can see, so the person who was asking about, what do you do with these speakers? Well, we've treated the room up a little higher than in those theoretical diagrams. This is actually what we did there. The mixer that works in here all the time absolutely loves the room, says it sounds amazing, and has done a bunch of great award-winning movies in here. That's the front wall. Not a lot of treatment on the front wall, just some low frequency absorption to control the back wave of the speaker to make sure it doesn't bounce back in the room without some control. Acoustically transparent screen, of course. This is the right wall. Diffusers, absorber, a door with some absorbers on it, a thinner absorber, diffusers, absorber, diffuser, absorber. So this practices what we're talking about, which is absorbers evenly distributed around the room, some up higher in the taller part of this room, and then interleaving with some 2D diffusers, 3D diffusers towards the back.
Anthony, I'm sorry, something caught my eye, and this is, I don't think this has come up in any of our conversations. That is a door in a mixing room, so I would assume that that's like a specifically made or a certain thickness, or the hinges are super heavy duty, the handles are super heavy duty to stop that door from rattling.
Well, more so, yes, but to stop the door from leaking sound. So this is a sound door, 300-pound slab on massive hinges with a big latch set, with massive gaskets all the way around it. So when you close the door, it's actually a magnet. It's a pair of dual magnetic gaskets. The door gaskets are like big refrigerator gaskets. Your fridge has a little magnet inside it. So you close the door and the magnet sucks up the door and closes. Yeah. And no, that thing's not going anywhere. It's not rattling. It's 300 pounds.
That's awesome. That's cool.
So that's the back wall with a fair amount of absorption towards the middle, a little scattering in the middle here, scattering on the outside. And on this particular room, I don't have pictures. You can go look at the Grimani Systems website and you'll see it. They left these diffusers exposed because they're so cool looking. There's this solid wood, beautiful thing. So that's the ceiling in this room. So again, this is where the front speakers are. These are the top channel speakers, and then all around the front part of the room is absorption. The back is diffusion. So that's the one place where we will kind of cluster more absorbers one place and diffusers in another place, and that's we want as much. We basically want as much support of the diffused energy of the surround speakers possible towards the back of the room. That's why the back is done that way. Okay, totally different room. This is a private screening room or a home cinema. 2 rows of seating. That's the kind of the rendering. Very comfy. Rather than use theater seats, it's really couches, really nice, comfortable couches. This is the schematic view of it. Let's look at the layout. So there's 3 speakers behind the screen. These happen to be our Grimani Systems Delta speakers. There's the icons of what's on the walls. This is the peeled out view again. This is the ceiling. And this is the back wall. That's the front wall, left wall, right wall. And let's look at the walls individually. This is the left wall. Absorber, absorber, absorbers, absorbers. Okay, I know at first it looks like a lot, but again, if you take them off the wall and you put them all right here, it's about this much of the room, under 20, 25%. Diffusers, a fair amount of diffusion over here because the ceiling is pretty tall. Surround speaker over here. And there you go, some 3D diffusers towards the back of the room. I have 200 pages of this, and it's going to start to get boring and repetitive, and that's what's great. because you actually are going to start to see a pattern of what works. So
Right.
now, I do want to say, to defend our science, is we've now done 1,000 rooms. I always listen to the same damn program material in each one of the rooms, whether I go do the calibrations or my chief engineer Manny Lacruba goes and does the calibrations. In the end, they all sound about the same, and the same
That's the
being
point.
reference.
Yeah.
Right. And reference being the mix room in which we heard these tracks.
Right.
Both Manny and I have been in mix rooms for a lot of part of our life. We know what the tracks sounded like over the original environment, and that's all we're trying to replicate. So, all right, so this is the left wall, that's the front wall. Some low frequency absorption around the speakers. You may notice this looks kind of like the mix room we were looking at before, gigantic films in New York. This is the right wall, diffusion, absorption, diffusion. This is 2D diffusion, absorption, 3D diffusion, absorption, 3D diffusion. I'll go back to the left wall. Notice that on the left wall, the first thing was an absorber. On the right wall, the first thing is a diffuser.
Right.
Okay. And that's because we have found repeatedly that an asymmetrical layout of treatments is better. The right wall globally has the same amount of absorption and diffusion as the left wall. I notice I lost my audio connection, so I'm going to be quiet for a second.
Anthony, I actually, if you can hear me, I didn't lose you at all. Maybe it's just on your end. Oop. So thank you, guys. It looks like there were a couple more questions that came in, so I'll definitely get to those last couple questions as we get towards the wrap up here.
And I'm back.
Yep, I got you back. Yep.
So Jason, there's a little flag that pops up that says that the audio is lost. So
I see.
What's the last thing you heard?
You were talking about the rooms, the acoustic treatments not being symmetrical for a reason.
Right. So this asymmetry. So overall, the left wall has the same amount of, more or less the same amount of absorbers and diffusers as the right wall, but they're laid out slightly differently, so that when you're in the middle of the room, the pattern that comes off the left wall is slightly different than the pattern on the right wall. If it was identical, you would misinterpret the wall reflections as an intentional sound coming from the speakers. When your brain hears a correlated sound coming from the left and coming from the right, it thinks that's an intentional sound. There's a lot of science, there's a lot of research on psychoacoustics. I talked about this, I think 4 weeks ago. Somebody asked the question about who was the researcher that showed this. Greek mathematician or Greek psychoacoustician. I haven't had time, I'm sorry, to pull up the reference to it from either the university in Athens or Thessaloniki. There's a guy in Argentina who's been doing amazing work. His name is Alejandro Bidondo, who's been doing amazing work on the texture response of rooms. He's also been working a lot of this. So there's work done by people on this. I basically don't even come up to the heel of what these guys have been doing over their years. So you can read that. You can read all that research by looking them up. Okay, I'm still here, right?
Yep, you're here.
All right, so this is the back wall, cluster of absorption towards the middle, a cluster of 3D diffusion towards the outside. On the door, we're going to put some absorption, because putting a diffuser on a door is deep and challenging, because you can't open the door without it banging into the wall. Yeah. That's the ceiling, cluster of absorption towards the front, cluster of 3D diffusion towards the back. By the way, all these lines are stretch fabric seam lines. So in this room, actually, I'm gonna go back over here. In this room, this is a stretch fabric panel. This over here is the seam where the stretch fabric is tied back together. There's a panel of fabric here, a panel of fabric there, panel of fabric there, and that is actually mounted on a very simple skeletal framing that holds the stretch fabric track away from the wall.
Sure.
The stretch fabric looks like this, or the track, I'm sorry, the skeletal material. There's a back plane made typically out of 3/4 plywood or 1/2-inch plywood, cut to about 4 inches wide. There's kickers made out of just 2x4 material, so 3.5 inches wide. If you're building a stretch fabric wall that's 4.5 inches away from the wall because you're hiding 4-inch materials and speakers, this whole thing needs to be for about actually 3.5 inches, because the track is 1 inch deep. That's the actual plastic bead.
Oh, I think we Oh man, Anthony, did I lose you? Anthony, I can see your
And
mouse.
we're back.
Oh, yeah, I say I can see your mouse moving. There you go.
All right. So this is how we designed that skeletal material, that basic framing to hold out the stretch fabric track. The track is typically 1 inch deep. So you just need to size these kickers as blocking kickers so that it all works out. Okay.
Right.
It's just one way to do it. There's other ways to do it too. All right. And then you build it out by first building out the framing, put the materials in there, stretch a fabric in it, and there you go. All right. This is another room, something we just finished recently, also an Atmos room. This is a top view of it. This is showing the listening angle. This is the right wall. This is the front wall. This is the right wall with treatments. So speakers, this happens to also be our Grimani Systems beta speakers. Oh, I think this is a room that is going through construction now. I'm wrong. Yeah, this is actually in mid-construction. So beta speakers in the front, our Delta speakers for the sides. What you see in red is actually the decorative framing. So there's a pilaster. Can you see that there, Jason?
Yeah,
There's
yeah.
a
Yeah, you can
little
see the length
icon
there.
here for a sconce.
Right. Looks like there's two of them in
Jason,
there. Oh,
yep.
can you hear me? Yes, it looks like there's two of them in there flanking those that center section of speaker and panels.
Right. So this is all woodwork that you're seeing over here. In the middle is a fabric, basically an opening with fabric tracking into which we're going to put treatments and speakers. So again, absorber, 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 diffusers, 2D diffusers over here, 3D diffusers towards the back, some low frequency absorbers in the lower panels. This is the front wall where we're putting low frequency absorbers flanking the speakers. This is I'm sorry, the other one was the right wall. This is the left wall. Diffusers, absorber, diffusers, absorbers. Note the diffusers, we're taking them up pretty high in this actual implementation. This is the back wall, absorber, absorbers, some 3D diffusers to the side of that and up top. And then in this door is going to stay untreated because of the construction of the door. This is the ceiling, cluster of absorption towards the front, cluster of diffusion towards the back. Okay, this is a peeled out view of all of the above. And this is a room, to be clear, that doesn't just have stretch fabric everywhere. When you walk in this room, you're mainly going to see the woodwork, chair rail, pilasters, baseboard, crown molding, and then insets of fabric, and it's going to look really good. I'm going to finish with this one because this is an odd shaped room. So this is something we just finished in Park City, Utah. Client moved into this house, had a
Oh, did we lose you, Anthony? We may have lost you. And are you back? Oh, I thought I heard you for a second. Let's give him just a moment. Sorry, guys. I don't know if there's just a bandwidth problem or what it could be. We were going good there for a while. There's another question that came in that I want to definitely make sure we ask, and that's what kind of acoustic treatment do you put behind acoustically transparent screen? I've seen a lot of theaters I've worked on where the speakers were behind the screen and they were in their own little kind of cutouts or their own little cubby holes, if you will. So that's an excellent question. We'll make sure to get that question out to Anthony. Just give him another few seconds here to hop back on. Sounds like we may have just lost his mic. Stand by. And other than that, guys, if you have any last minute questions, go ahead and get those typed in because I think we'll be wrapping up here in the next few minutes. So if you do any last minute questions, feel free to throw those in. You can see him switching his screen. And I think he may
And
be
I'm
back.
back.
And
Woohoo!
he's back.
That was a long.
No, that's okay. I just let everybody know if they have any other last minute questions. I think we'll be wrapping up here pretty soon. And one did come in, so I'll wait till you're done here to ask that one.
Sounds good. All right. So this is a smaller room with a really odd shape we did for a client in Utah. So look
Mm-hmm.
at this. It's like this. You know, I should have. I think I did. I may have used this for the presentation on layouts and odd shape rooms, but this is funky. Well, we made it work in the end
Mm-hmm.
uh, through proper treatment, proper speaker placement, lots of time spent in tuning. It took me about
Mm-hmm.
3 days to tune this room. It
Sure.
sounds like an amazing bubble. Amazing.
Yeah.
So this is the left wall. And to be clear, the left wall, let me go back over this way. This is the left wall. It's this zigzag
Oh, weird.
of
Yeah.
odd shaped space, right? On this left wall, we're going to be putting, there's some diffusers, a bit of absorption, some 2D diffusers, absorption, 3D diffusers, and an interleaving of loudspeakers with all
Mm-hmm.
that. This is actually all of our Grimani systems, I think a system 4 package.
Here, did we lose you for a second? Oh, sorry, guys. Sounds like we may have lost him again. Must be some bandwidth problems. Oh, I think I got you back.
Okay,
There you go.
I'm back, guys. So I'm almost done, almost finished over here, and I'm noticing that well, it's getting flaky, so I'll just finish up, okay? And then it's going to be time for lunch. All right. So left wall absorbers, diffusers. Right wall, some absorbers, some diffusers, interleaved again, some 3D diffusers towards the back. This is the front wall, which again is sort of odd looking because what you're actually seeing is the zigzag of the walls going around over here. Front speakers are actually, okay, I think I'm back.
Oh, there you are.
Jason.
Yep. Yep.
Wow, this
I
is
lost you for just
crazy.
a second. Yeah.
Yeah, really annoying. So front speakers are mounted on a baffle wall over here because the odd shape over here, we actually brought them out from this little cave. But some absorbers placed along the front part of this. The back is some absorbers in the middle, some 3D diffusers over here, and this is the ceiling. So again, this room is oddly shaped. We put the speakers here instead of them being all the way in the cave.
Mm-hmm.
Cluster of absorption over here, cluster of diffusion over here. The reason that front wall looked like it had all these absorbers and diffusers is we're representing this entire thing, right, as the front surface as seen from the back.
Right.
And there you go. So this room, completely odd. This is one of those where you would open the door and go, nope, not going to work.
Oh boy.
And it was given the missions like, make it work the best you can.
Yeah.
Whatever. This is the room. If it's not good, it's not good. Just do the best you can. And like I
Mm-hmm.
said, good speakers, good acoustical treatment, and plenty of tuning time. And then the client is like super happy.
That's all that
Now
matters. Excellent.
I want to do one more room in which I want to show one thing I did not have time to talk about, but is a little trick we love to do. So I'm just zooming forward through tons and tons of rooms. Yeah, okay. So this is a room where we did this one thing, which is, first I'll show you actually I'll go to the treatment lateral view of the room. So here's another room, you know, 2 rows of seating, speaker, this is a wide channel speaker, absorption, 2D diffuser, absorption, 3D diffuser, all of that, right? Starting to look familiar.
Oh yeah.
Front of the wall is using our Deco absorbers as low frequency absorbers. The right side is 2D diffusers, absorbers, 3D diffusers. All looks pretty familiar. The back wall is absorption in the middle, 3D diffuser towards the outside. But this room has an extra little trick that I didn't talk about, and I really want to conclude with, which is we were given the opportunity to put some absorption in the floor at the front. I call that an absorption pit.
Very
right?
cool.
So where you actually build the room with a recess in the middle to catch the first reflection off the floor nice and deep. And the riser was also turned into an absorber by perforating about 1/3 of the riser with some holes. You have to calculate what the perforation ratio is and the depth of the riser to make this into a big base absorber. So you can't really see it here, but this portion of the room is actually a pit with treatment. It's covered with a grill, covered with carpeting, but the low frequency of a broadband energy of the reflection that would otherwise go pink, pink is absorbed here. And then the whole riser is built into a base absorber. And you'll notice in a lot of these rooms that there's not a lot of base absorption visible in the walls because we've put it in the
It's in the
riser
floor.
or we've hidden it somewhere in the floor somewhere else. So that's a little trick that I will leave you with. That does mean that you're getting involved in the project early on,
Way
very
early,
early
yeah.
on, so that you can actually influence that. I'll finish with some eye candy. This is a huge room we're doing in Indonesia right now. Lots and lots of speakers.
Oh, wow.
Massive, massive, massive. Lots of seats, big low frequency absorption, giant ventilation system. That's what the treatments look like in here. Lots of different absorbers and
Wow.
diffusers, lots of speakers, lots of channels of Atmos. It's going through construction right now. I got to go back to Jakarta when all of this worldwide challenge of pandemics goes away, and
Sure.
we'll finish this out. So, all
That's
right,
excellent. That's a
enough
beautiful room.
enough of this. Enough of this. Here, I'll leave you with this. All right, guys, you have been amazing at sitting through 2.5 hours. Oh my God, of this blah blah blah
Yeah.
on absorbers and diffusers. Thanks so much for hanging. We'll
There's so much to learn. We could sit here for hours more, I'm sure.
Yep, go ahead.
Easily. I'll say we
Oh,
could
I lost
easily.
you again.
Oh no. I was gonna say, do you have me back now? A little bit? No? Yes?
I'm back.
Maybe?
I'm back. I'll
Oh, you're
take a
back.
few questions if there's any left. Otherwise, we'll just need to do it
Yeah.
through.
Sure. I've got two questions, and I'm gonna leave my camera off just to save the bandwidth. But number one, which acoustic treatment do you put behind the acoustically transparent screen? I've seen this plenty of times in the past where somebody has speakers and they build them into kind of a cavity, if you will, behind the screen. What kind of acoustic treatments do you put back there?
Yeah. So one option, if you're building a whole baffle wall, like in this room, is the entire baffle is lined with 2 inches of what's called line acoustic or some other mid-density absorber. On a number of the other designs, let me go back to that. I've shown what we're putting, which is, there is not a baffle. This is the front of the room. There's an acoustically transparent screen over here. Where these particular speakers don't need a baffle wall. Our speakers are built to go on a wall, and we're just putting absorbers, preferably low frequency absorbers, so as to not suck out too much highs out of the room in a useless way. Let's see if I have another room example. Coming up. Did that one show it? Yeah, so here again, we've got some absorbers flanking the speakers to get, basically what we're trying to do is put some deep absorption so that the low frequency energy that would otherwise radiate off the wall doesn't get re-radiated, or the lower mids. You actually want the wall to act as a low frequency reinforcer, but you don't want it up into the mid frequencies.
Awesome, awesome. And then last question. Let's say the client wants to do theater and 2-channel without an
Yeah.
acoustically transparent screen. He says, how would you treat the front wall if the client did not want to use an acoustically transparent screen? Can you put the absorbers behind the screen, or where would you place them if they want to use the theater room for, again, theater and 2-channel?
So I have found, by the way, that there is not a contradiction between what you need for 2-channel and multi-channel. I don't call it theater versus music. It's 2-channel versus multi-channel. Okay.
Sure.
A movie could be 2-channel. Somebody could decide to make a whole movie in left and right channel. It would
Good
be
point.
stupid, but they could do that.
Yeah.
Or music should be multi-channel. Why restrict it
And we
just
see
left and rights when you can also use other speakers that can help? That being said, I don't see any need to do any difference between the two if you design it right. Right, so if you follow the guidelines of that 15% of absorption, 20% of diffusion, the room is going to still have some liveness. It's going to sound great in 2-channel. It's going to work. So the question though was, if my speakers are, was it actually if I'm not using
like
an acoustically transparent screens and the speakers are in the room?
Right. Yeah, you don't have an acoustically transparent screen. So what do you do then with the absorbers and diffusers?
Um, well, if you don't have an acoustically transparent screen, the only thing that's behind the screen is a flat wall. You
Right.
could still put some low frequency absorption, because the material of a screen, even if it's not acoustically transparent, is essentially transparent. I would say below 800 hertz or something,
Hmm.
600, depending on the type of screen, 600 to 800 hertz, it lets the sound right through. So you could still use that surface for low frequency absorption, and you should.
Got it. And last question is more of a comment, and I will definitely agree with this. That was awesome. Thank you, Anthony.
Oh,
So
thank you
guys,
very much. Thank
uh,
you very much.
yep, that'll do it for today. Any other last questions that you may have? You know, maybe you're sitting around tonight, you think of another question. Guys, feel free to send those questions to me. I'll get them over to Anthony. It's jason@avproglobal.com. We'll get this episode up on YouTube in the next couple of days. You can share it around with your friends and colleagues and go back and probably watch it one or two more times to, no pun intended, absorb some of the knowledge here that Anthony's passed on to us. So with that being said, guys, that's it for today. Thank you again, Anthony. Enjoy the rest of your day, and we'll see everybody on the next one.
All right, everybody, take care. Thanks for hanging.
See ya.